of presentation. And also, as a result, it also will be much less mathematical to a sense. So Sudhir asked me to, or suggested that I talk about distributed storage systems. So for this one, what I have decided to do is I just want to explain a little bit what this topic is about. So my main goal with this lecture is for those of you who do not know what coding for distributed storage is about, just to give you the main feel of what is different, like what is it that we care for storage which is different than for normal communication. And also somehow this topic was very popular quite a few years ago. So I am not pretending at all to give an overview of all the work that has been done. Instead, I just want to emphasize more where it came from. And also because it's a topic which is still coming from engineering application, I will try to still give, up to the level of my own understanding of the engineering part, some kind of pointers as where it's useful, why it's useful, and what are other considerations that coding theorists may or mathematicians may have in mind when they look at this kind of topic, or how they may want to talk to engineers to maybe get a better sense of what's going on. Okay, so again, it's going to be more, it's going to be more about me telling you a story about where the topic came from, what motivated it, how it evolved. There won't be so many proving or theorem or a few computation here and there, but just to get a feel of what's going on. Okay, so let me just adjust one thing. All right. So again, I don't mind actually if someone has an urgent question and you want to ask by any means, feel free to drop a line on chat. I'll keep an eye on this. Okay. So I want to discuss a little bit about what is distributed network storage, a very rough feeling about it. Just to give a sense of what is the context we are interested in, okay? Because when you do a basic coding theory, probably there is a point where in some class or someone tells you you have a transmitter, a receiver, you have a noisy channel. So just some kind of feel of where the problem is coming from. So for the case of distributed network storage, the idea is that we want to store data. So sometimes we say we have a data owner, someone or some entity or some company wants to store data over a network of nodes. Okay, so here I would like to emphasize the term network of nodes because it doesn't just mean that we have different nodes. You can visualize computers or hard drive. But the term network refers to the fact that we want to store this data, but the nodes are really connected among each other, and the fact that you have to connect them actually plays a role. The reason why I'm emphasizing already this at this point is because you have also coding for storage for other type of storage system where maybe the network connections plays a little bit of a role. So the typical application usually people have in mind when they consider this kind of storage problem, they are thinking possibly like data center, or archival in peer-to-peer network. And the overall idea is that, for storage, we need a redundancy. It's necessary or it's essential for resilience. What I mean by this sentence is redundancy means that whatever you store in some manner, you will store it more than once. And it's essential for resilience, meaning for the system to be resistant to whatever may go wrong. And typically, it seems that things tend to go wrong rather than the other way around. So I have tried to put some statistic that I have found online about some, here it's a storage company that were looking at different statistics on the type of failures they have in their hard drive. So the idea is, okay, you store data on a bunch of hard drive, and whenever your hard drive, whenever something goes wrong with your hard drive or your system in general, you lose your data, or you may lose your data if you don't have a backup, which is why the term redundancy. And so failure can happen for a bunch of reasons. It may be a hardware, so really the hardware that crashes. It may be a bug in your software. It can be your network connection that dies, or it could just be a human factor. Someone was supposed to replace a hard disk and it's not replaced properly, or whatever are the reasons. So the assumption is, okay, you have a network of nodes, you are storing your data, but if you just keep a single copy of your data, chances are you are going to lose it because something will go wrong. And so you need to have redundancy in order to prevent that from happening. Some statistics that I used to show when I used to be more active on this topic, but I still think it's actually quite relevant, is that some numbers. Okay, so I will not describe too many of the numbers on this slide, but I think when people consider storage system, or even just for normal user, it can be an interesting exercise just to think through it and get an idea of the amount of reliance that we have actually on cloud storage or data centers. If we look at all the activities, including this week's workshop, where we rely on someone storing the data for us. This visualization that I found it actually pretty interesting. It was already in 2017, and so about 3 years ago. You can see what was happening every minute of the day in terms of cloud storage resource usage, the number of tweets that people were sending, the number of users on Skype, the number of users on Instagram. You can just have a look at this slide if you are interested later on. So it's really a number of data that is past imagination by now. Okay, so this is really important because it's not just interesting as a societal development, it's also very interesting because somehow it kind of explains why this topic of coding for storage developed, and I'll get back to it a little bit more later. But the fact of the sheer volume, increase of sheer volume that we are looking in using of storing data somehow also triggered this whole bunch of research on the topic. Okay, so now let me try to go something a little bit more technical. So let's try to understand when you are looking at, I see a typo in the title, coding for communication versus storage. In communication, we are very familiar with the idea of redundancy. It's also very important for storage, but there is another concept which I think is probably the most critical to understand if you are new to this topic, is the notion of repair. Okay, so there are lots of nuances to this notion of repair, but really understanding the difference between the two topics, I think, is really the key thing that I hope you will take away from this talk. So the idea is we need redundancy. So redundancy meaning when you store data, that means your data will be present more than once or more than twice or more than 3 times, but at least certainly more than once. And the idea of using redundancy through coding, if you're a coding theorist, it's very natural because you have been studying how you can add redundancy by adding parity to your information symbol. And somehow for the storage community, for a really long time, just considering replication, so that is in terms of code, you can think of the repetition code. So just keeping several copies of your data was really a good solution. It was a really good solution because it's very good for availability, meaning when anyone is interested in reading his or her data, you can easily, just read it. It's good also in terms of durability. So you can easily keep your data, the several copies of your data. I mean, I'm saying easy, okay. I mean, relatively easy, I guess, compared to what we will see later on for coding. But, and there is a but, it's actually very costly in terms of storage. What I mean is that, of course, if you just make a copy of your data, if you have whatever file which is 1 terabyte, well, if you want 3 copies, you'll use 3 terabyte. There is nothing much that you can do about it. And this used to be not so much of a problem simply because, as long as we were not storing that much data, it was still manageable. But now the problem is the society is really producing a huge amount of data. And so if we have to actually keep 2 or 3 copies of every piece of digital data that we have, it's actually very costly. So that is why erasure code came into the picture. So erasure code, we know from coding theory, they offer a good compromise or a good trade-off. If you look at, let's say, in coding theory, we understand in terms of rate and reliability. So the same thing can be translated for storage. So the storage cost is basically the rate of your code. And availability, you can think of that, or reliability in terms of your Hamming distance. So we know that erasure codes, you can get very good erasure protection and at a very good rate. So in a sense, it looked pretty natural that it could have application to storage. So when I started to work on this topic quite already a few years ago, I really had to make a pitch that this was making sense. But by now, really, every major cloud storage company is using erasure code one way or another. So it could be Google distributed file system, Colossus, or Microsoft Azure, or now you can look at also system by Huawei and so on and so forth. They all are using erasure codes in their data center one way or another. Okay, so let's try to understand how we are mapping erasure code into a storage system. So when I was describing yesterday an erasure code, so I was really looking at it from a more mathematical viewpoint. So I was looking at a k-dimensional subspace, some sort of vector space of dimension n over a finite field. But more here, I will give a pretty much equivalent definition, but much more down to earth. So you basically have a map. You have a k input symbol. So in the context of storage, it will be blocks of data. It's your information symbol in coding theory. So your map will take these k blocks of data and will input n blocks of data, meaning that n minus k, typically the parities in your code words, that gives you your redundancy. And we know that once you use a linear code, so we can characterize it by its dimension and its length. And so it's characterized by how many blocks are needed to recover k blocks of original data. Or in other words, you can, the error or the erasure capability of your code tells you, given a number of erasure, like how many can you tolerate? And everyone who has taken the first basic course in coding theory has seen the singleton bound, the concept of maximum distance separable code. And so you know that you have a bound on how many erasure you can recover from. And you know there is a trade-off between the redundancy, which is also the rate, k over n, and this erasure protection capability. So it's really like the trade-off between n, k, and d. And so you can really, so that's a viewpoint that we can actually, that we will adopt for storage as a first understanding of what's going on. And so when people were looking at coding for storage at the beginning, they were often describing, you can find what they call three-way replication, which is basically a repetition code. So a 3-1 erasure repetition code. Okay, so let's see a bit more precisely how are we mapping an erasure code into a storage system. So for communication, so what I will do is I will show 2 diagrams, which are basically the same workflow, but one will be the one you know that we usually use for communication, and then I will show the same workflow, how we can translate the communication component into the storage component, if you wish, like from an abstract viewpoint, to try to understand what's going on. So if you look at erasure codes for communication, so we have some message, some vector of symbols we want to transmit. And so we usually model it as K blocks, K information symbols, or K blocks for coding, typically K symbols. And well, we do our encoding into N symbols, which will then be sent through an erasure channel. So the best analogy, I believe, is considering erasure channel. So we can also consider errors, but typically erasures. And so, okay, so you have the middle part with the red star showing erasures is the important analogy, but this is also where the difference will happen. So you send your code word, and you have a number of symbols which are erased. And as long as the number of erasure is okay, with respect to your minimum distance, you can recover your information symbol, reconstruct your data. So this is our normal transmitter, receiver, noisy channel, or more precisely erasure channel that we are familiar with in coding theory. So how does it fit the context of a storage system? You can, at an abstract level, really look at a very, very similar workflow. So now your message or is your data object, the thing you care to store. At an abstract level, we don't really explicit so much how this is actually stored. So we just visualize something which is like K symbols over some alphabet. Then we could imagine that, okay, we are going to do an encoding like a normal erasure code that will give us N coefficient. So for communication, they are like the N symbols to be sent over your noisy channel. But otherwise, for storage, there will be N pieces of data that will be stored across N different nodes over your network. So this is stored in storage devices in a network, typically different storage devices. And now you can imagine that any failure of your system, typically a disk failure or a network failure affecting some of your disk or a software bug, any one of those basically means erasure of one data symbol or one data block. So then we say, okay, so if we have some data blocks which are erased, as long as enough of them are left, we can decode, we can reconstruct the original data blocks, and therefore our data is still there. So the analogy of having erasure and recovering from this erasure, the way I showed the model here, very abstractly, it really looks very similar to what was going on, for communication. But here comes the main difference. So the main difference is this notion of repair. So what is this notion of repair about? The process in communication is, so the way I look at it is considering a temporal dimension. So in communication, it's like an instantaneous process. So your transmitter sends something and the receiver gets something, and the receiver handles the received code word with whatever number of erasures are there. But in a storage system, it doesn't work like that. You do create your code word, but then erasures, they happen over time. So maybe you created your data, you protected it using an erasure code, and maybe after 2 months, a first disk crashed. And after another month, you had more failure. And after some other months, more failure, and so on and so forth. So what this is saying is that, well, you start with an amount of redundancy, the number of parities that you use for your code word. But over time, if you do nothing, every failure that happens, remove some of your redundancy, so remove some of your protection. And eventually, if you do nothing, you will just lose your data. Even if you make 3 or 4 copies of your data, if you just, okay, you lose the first copy, it's still okay. You lose the second copy, it's still okay. But after that, you lose your third copy and you have lost your data. And so whether the data is lost like permanently because of failure, or maybe because your nodes may go offline because you are looking at something which is connected, the data is unavailable. And so this leads to this notion of redundancy needs to be replenished. Being replenished meaning that you have to recreate it one way or another, so that you can keep your protection over time. So the analogy that I often give when I explain this is like, imagine you have, I don't know, let's say some very important work going on your computer, and you do not create any backup. If your computer crashes, you loses everything. So if you are scared of using your data, you typically make a copy, let's say on an external hard drive. But if your external hard drive dies, you have no choice than buying another hard drive and recreate a copy to make sure that your copy is still here. Because once your hard drive crashes, if your computer also crashes at the same time, you have lost everything. So this process is really what is being called a replenish redundancy. Okay, so and this is really the very distinguishable feature of looking at storage versus communication. And this is actually why I think the storage community took really a while to move to erasure coding. It's not that they didn't know about it. It's just that somehow, for the reason I'm going to explain on this slide, if you use a very powerful code, like let's say MDS code, the repair process is not so obvious. So let me try to explain why. So if you use the MDS code, the procedure is pretty much as before. You have a bunch of data symbol. So you encode them. You create your N code words. But now what happens is that if you lose some of them for whichever reason, well, you will have to recreate them one way or another, because otherwise the next round of failure, you may lose everything. So the problem is that for an erasure like an MDS code, you need all your information symbol to recreate one parity. So if you lose, let's say, a single data block, you will still need to take data from all your information symbol blocks, and you will have to recompute everything in order to rebuild the one coefficient that you have lost. And that, from engineering viewpoint, is not so trivial, because your nodes are busy doing a bunch of stuff. They are over a network, so you have to really use the bandwidth. You have to, first of all, the nodes themselves must be available. Then you need to use your bandwidth to get all your data. Then you need to do all the computation. Then once you have computed, you need to send it back to whichever nodes have wherever the new data will be stored. And so it's not that it's an absolutely bad strategy in itself, but it's more a strategy which is working if you can afford to wait for a while. So you wait for a while, you have enough failure, then it may be worse. You just do a batch processing of all your failure, and then you do it like that. But that means you must have a level of confidence that you are not going to lose your data while you repair it. And so for actually this reason, again, I believe it took a while for the storage people to seriously consider looking at erasure code. And on top of that, it's slightly more complicated than this, because, well, not only you want redundancy so that you don't lose your data, you want to be able to repair your data efficiently, but you also want a low storage overhead. Simply because that's, well, the whole purpose of using erasure code is to replace replication. So it has to be good in terms of storage. And yes, you may want to use very little bandwidth when you have to do repair. And you also want the repair to be very quick, so that you prevent failure to happen during this time. And you want little computation also for the same reason. So there may be actually a bunch of reason behind that really for a while was slowing storage people to consider erasure codes. So just to give you a timeline, actually you can see if you look in the literature, people have been getting this idea already quite some time ago. So some ideas of using erasure coding were already present. You can see this Ocean Store paper already almost 20 years ago. Around the same time, you can see that people were already discussing. So in this paper, erasure coding versus replication, we're wondering, is it worth it? Yes or no? And then something that really changed the, let's say, research landscape was the interest in the coding community about the topic of network coding. And so the idea of bringing network coding, for the coding people in general, gave some inspiration to this group of researchers to actually consider a network coding approach to storage. And so from there on, a number of papers started to look around this topic of storage, coding for storage. So let me try to just give you a little bit of an idea of this main work related, the main idea behind the work that got inspired by network coding. The idea was to consider some information flow. So you would have a network with a source and a data collector. And so you would visualize the process of storing data as an information flow. So from the source, the data you want to store would be going to the storage node. So they are represented here. And from the storage node, the information will flow all the way till the data collector when the data collector wants to read or access this data. And so by using this idea that you have a flow of data that goes from the source to the destination or the data collector, so the way you would do that is you would use MDS code at first as the first idea to store the data in the nodes. Then you will look at the information flow, and because it's an information flow, the author proposed to use a max flow min cut bound on this network. And the smart idea was that the way you define your cut in your network would involve cutting two types of edges. So one type of edge that is represented here. So what you would do is you would represent a node itself as two abstract nodes so that you could put an edge in between those two abstract nodes to represent the storage capacity of your node, so that you could allow the cut to involve the storage capacity. And then there would be another cut that would involve cutting edges used when a data collector or when there will be a need for repair. So when some node would need to contact the other in order to repair, the cut would actually also cut these edges. So in doing that, they were able to get a trade-off between the storage overhead and the repair bandwidth. So this idea led to really a number of research papers trying to understand how you can best build codes for this context. And this idea was extended in a number of ways. So this work is actually some work by a group of French researchers where they started looking at variation. So for example, a collaborative way to do this where it's the same generalization of model as before, where nodes were allowed to collaborate among each other as part of the repair process in order to hopefully improve the trade-off that were derived in the previous scenario. And the advantage of the collaborative approach is also you could tolerate multiple faults at the same time, while the previous approach was more trying to do it one failure at a time. And there were really a number of concepts that researchers looked at theoretically in this context. So, for example, they look at this idea of, okay, so if you want to reconstruct data or repair your data, they brought in this notion of functional versus exact. So what it means is that exact is the one we imagine, namely, if you lose a sequence of 5 bits, you want to recover the exact same sequence of 5 bits. But functional was more inspired by some information theoretic argument that as long as the same information is there, maybe not in the exact same form, it's still okay. Then there was question about simultaneous repair, or whether repairing one failure at a time, whether several failures at the same time, and different consideration like whether you actually need to really compute or whether you can just store data in such a way that you can just exchange the data that you have and still repair your data. So the small example I have shown here is like, you notice that the way the data is stored is you have 5 nodes, and V1, V2, V3, V4 correspond to actually up to V9. They are your what define your code, and O is the object that you want to encode. So you can visualize the VI as the columns of your generator matrix. So when you do your encoding, you get a bunch of parities which are representing. And the edges, this star-shaped thing is showing that. So if you look at what the first node is storing information. It's storing the block OV1, which itself can be found here, and it's storing the parity OV2, which can be found here, and OV3, which can be found here, and OV4, which can be found here. So that would be a kind of scenario that shows that in this case, if let's say node 1 fails, this node can actually just retrieve every missing piece of data from the other 4. So that was kind of example proposed actually by some researcher from Bangalore. They were looking at this type of code construction. So okay, so now I want to discuss a little bit another idea, which is that of locally repairable codes. And again, just to be clear, there is really a huge amount of literature on regenerating codes. So I really cannot have the ambition to try to explain everything that has been done on regenerating code. I think the most important part for a 1-hour talk is to know the concept exists and to understand the motivation coming from network coding in terms of information flow, and to know a little bit about the different nuances that it brought to the problem. Okay, so locally repairable code. Let me try to explain a little bit what these are. So I will discuss pyramid codes, which is probably the ancestor of all this family of code. Then I want to say a few things about code construction and bounds. So this is going to be slightly more, a bit more formulas, but not that many. So I will start by motivating this code by just giving an example. So I will take, let's say, an 11.8 MDS code. So, okay, let's imagine we have a Reed-Solomon code, if you are familiar with Reed-Solomon code. Otherwise, just imagine any code you want which has the MDS property. For Reed-Solomon code, we know it's basically about finding a suitable finite field size for it to exist. So it's not really a problem in itself to assume the code exists. And so, well, we do our normal encoding. So you have your information symbol, when you ate your generator matrix, and you compute your code word. And here I'm showing it in systematic form. So we notice that we actually have 3 parities. So now the idea of pyramid code goes like that. So what we will do is we will retain the systematic pieces, so from U1 to U8, and then we will retain 2 of the non-systematic pieces, so 2 of the parities. So to say something, C2 and C3. It really doesn't matter which 2 you pick, so let's say C2 and C3. So now what you do is, okay, so the idea of the pyramid code is we will actually retain C2 and C3, but we are going to replace C1 by something. So what are we going to replace C1 with? Okay, we will actually split our 8 information symbol into 2 groups. So the first group, let's say, contain the first 4 and the second group the last 4. And now we will redo the encoding of our code word, except that we will put to 0 half of the information symbol, the second half. And once we obtain now our new code word, well, that will give us C1 if you wish, only the C1 which has been obtained by putting 0 half of the coefficient. So we will call this C11. And similarly, if you put to 0 the other half, you will get also the C1 code word, but the C1 coefficient, but adjusted to the fact that half the symbol were set to 0, and that will give you, let's say we'll call it C12. So now if we look at what we get, we moved from our normal Reed-Solomon code to a slightly different one. So everything is the same, but for the fact that the parity C1 now has been split, if you wish, into 2 symbols. And now every one of these 2 symbols, C11 and C12, they depend only on 4 information symbols instead of the 8th one. Okay, so I guess I hope the idea is intuitively clear enough. So instead of having one parity C1 that involves all the 8 information symbols, you have a mechanism to just split this into 2 parts of the same parity, each of them depending on only 4 information symbols. And so this gives rise to the construction of pyramid code. So if we understand the small example, we can do that in general. So in general, you start with your favorite MDS code. You will have your key information symbol that you will split into a number of groups of your liking. And okay, I'm going to explain this on the image here. So your code word has n minus k element of redundancy. So what we do is that, okay, so this part here represent your data. So you will look at, so you have cut your data into a small group K1 up to KL. And then what you will do is, okay, so first of all, you will keep out of this M symbol, keep M1 of them. So this is the equivalent of keeping C2, C3 on the previous slide. So you have your normal parities from your Reed-Solomon code. So you just keep a number of those. So that would be what we call a global redundancy. So just your normal parities from your Reed-Solomon code. Now, the other one, what you want to do, you will actually compute new, what are called local redundancy for each of these groups. So you will do exactly the procedure that was done on the previous slide. So you set everything to 0 but the group you care about. And for the group you care about, you recover the corresponding parities. So that will give you a number of what are called local parities or local redundancy. And you will have one such local group per group of symbol that you decided. So we can see in the group here. So you see the first index from 1 to M0. So 1 to M0, it's actually computing this M0 local redundancy for each of the symbols. So the second index gives you, this is the first group up to the S group. So now if you do this construction, you can actually, turns out you can actually figure out the minimum distance. So if you create a pyramid code in that manner from a NKMDS code, so you can actually recover, you can compute how many erasure you can recover. Namely, you don't change it in the construction that has been shown with respect to the MDS code. And each group itself actually is a MDS code, the way it was created. So, of course, we may already perceive that a good thing is that we can keep a level of fault tolerance. The bad thing is we are increasing the storage overhead of the rate of our code in doing that. And so one motivation for this code construction was coming from what were called degraded reads. So that means, let's say some of your data has failed and your user really want to read the data. So you may want to really access very fast the data that the user wants, but the data itself is not here. So if you have such small groups of local redundancy, you may actually just be able to recover with a quick computation out of the local one what the user wanted. So in a sense, in this scenario, you are balancing the local versus the global. So the local repair are actually, well, cheap in terms of doing the repair. And the global are actually expensive, but the global are there to ensure enough fault tolerance, while the local repair somehow is more here to, help repairing your data. And so a particular family of code, which is called local reconstruction code, at least as advertised by the papers you can find online. So they are a particular implementation of pyramid codes, which are actually used in Microsoft Azure. And so what they did is to actually implement that in a system, what they needed is, well, it should be really good for implementation. So they wanted a small field size and over a binary alphabet. So that's actually an example I like to mention because it's one of these examples where you actually have a real implementation of some theoretical construction we can understand. Then I'll make a small couple of minutes of advertisement. So when I was looking at this already quite a while ago, as you can see based on the dates. So for me, what I thought when I look at this at the first time is I had in mind, well, Reed-Solomon code, which was the MDS case. And again, if you are familiar with Reed-Solomon code, you are probably familiar with their most natural interpretation, which is polynomial evaluation. So by then, what I thought was, okay, so if you can do a polynomial evaluation, then, and you want this property of repair, then there would be a way to do that. And the way to do that is by choosing your polynomial in a smart manner. So what I wanted is that actually to see whether it's possible to get this nice repair property. So that means you want to be able to, in a sense, involve few nodes in order to do a repair. And in order to do that, I thought, okay, maybe we are just going to do the following thing. We are going to take polynomial evaluation, but the polynomial will not be any polynomial. It will be what we call a linearized polynomial. And a linearized polynomial is a polynomial which has actually the property which is written here. Namely that when you evaluate it in a sum, it's actually the sum of the evaluation. So this, I thought, would be a very nice way to look at this storage problem. And if you look at it, because from the storage viewpoint, so you will have a scenario like that. So you still have your file, k blocks of file that you want to encode. This slide shows what a linearized polynomial look like. So you can see that what is particular is the exponent, which is itself a power of 2, which explains why when you look at it modulo 2, you have the property that I described on the previous slide. And so what you will do is you will use this polynomial. So you will evaluate it to construct each of your blocks the same way you do with a Reed-Solomon code. But now you have that blocks can be really obtained as sum of each other. Okay, so I have put in my slide just one concrete example. If someone has interest in trying to try once to do this computation and see how it works. So in this small toy example, so you have a file that you can cut into 3 pieces or 3 fragments, which are the coefficient of your polynomial. Again, same thing as polynomial evaluation of Reed-Solomon code. Then you evaluate your polynomial in different powers of W. So here I'm choosing W to be, I'm working over some finite field. So W will be the generator. So I guess based on the number I have, probably I'm looking at, I need 2 to the 16, I guess. And then you just, you can actually compute the polynomial and look actually at what's happening. So once you have your code word, which is given like that, you can see, okay, so if I have a missing piece, let's say if my missing piece is just one of the, let's say P1, you can see in how many ways out of what you are left, you can reconstruct P1. And similarly, if you have two missing blocks, you can count in how many ways you can actually recover the missing symbol. And same thing if you have three failure. So something that I would like to show next is actually maybe a difference from the standard mathematical viewpoint on coding theory. So I'm also teaching a coding theory class this semester, and it's true that when I explain how you can recover from erasure, I'm using the Hamming distance, and I'm saying, okay, you can recover until a particular property of the Hamming distance, a particular value of the Hamming distance. So when people look at storage systems, they look at this notion of static resilience, and static resilience is a probability. It's a probability that an object in the system remains available without any further maintenance, so you don't try to replenish the redundancy, even when a fraction of the nodes become unavailable. And so what you see here is you have a number of nodes, and the number of and the availability of the number of nodes on the x-axis, and on the y-axis you have this probability. And you can see what's happening with MDS erasure code. It's really a binary type of behavior. So that means either you have or you don't have enough block left. And so you have a probability of being able to retrieve, which is either 0 or 1. So it's really a binary thing. It turns out that if you look at some of these codes that are being built for storage system, it's a little bit more nuanced. Namely, you have a regime where you get either everything or nothing, but you have a range in the middle where you have actually a probability of still being able to recover. So that means you can be a little bit more flexible in a sense in not accepting either everything or nothing, but actually still be happy to have a fairly good probability even when you cannot ensure a probability, which is 1. Okay, so now I would like to mention, so the title of this part was about locally repairable code. So I want to mention this notion of a locality. And I believe this was probably the next main important idea after that of looking at information flow and regenerating code. So I will give you a definition. So actually, this topic has also evolved. So there are more nuanced definition, but I will give you maybe the basic definition of locality. So if you take a code word, you look at its coordinate, let's say the i's coordinate, and you will say that it has locality R if its value is determined by at most R other coordinates. Okay, so we understand what it means. It means that if you have let's say a parity, this parity is computed as linear combination of a number of information symbol. But actually, this is a slightly more than just that. It's really by at most R other coordinates. So it could be either you are doing it using information symbol, but you could actually do information symbol and other parity also in order to compute this quantity. So this gave rise to this notion of a locally repairable, recoverable code. So this term locally is actually coming from, it got, I believe, the inspiration come from the theoretical computer science people who were looking at this concept of locally decodable code. But it reflects the fact that you want to, be able to repair your code locally. That is by accessing a number of coordinates in your code word. And so you can now parameterize your linear code. So instead of having the length, the dimension, and actually the Hamming distance D, you can actually add R as being a new parameter. And so that's a code that, as any linear code, will encode your k information symbol into a vector of length n. But now you want the property that for any symbol in the code word, there exists at most r other symbol, such that the value can be recovered from them. So in that case, so we move from having locality r for one coordinate to speaking of locality r for your whole code. And so locality is really this concept that tells you that if you lose a symbol because of a node failure, its value can be recovered by contacting at most r nodes. So the concept of locality r, I think, is a good abstraction. So if, let's say, now you tell me you are not interested so much in the understanding the storage system, but you are interested in the code design, it's a very clean way to formalize what you want for your code. On top of n, k, and d, your usual parameters, you add r, this new parameter that measure how good, in a sense, your code is for a distributed storage system. Yes, so I just mentioned that you can actually look at your code as being a n, k, d for Hamming distance, and r for a locality code. Something that I don't know how apparent it was from what I said earlier, but something which is clear is that the same way when you design MDS code, you realize that you have a trade-off between rate and Hamming distance. When you try to add this new parameter of repair, it introduces a new trade-off, because in a sense, if you want good repair capability, you want to be able to recover any coordinate out of a few of the others. And if you want to do that, typically you tend to have more parities and thus worse rate. So a nice result that was derived is that you actually have a clean bound. So for an NK linear code, so if you have locality R, it turns out that the following bounds hold. So n minus k plus 1 minus d is greater or equal to this quantity that you see here. So this shows clearly that, okay, once you give n and k, as usual, you can see the trade-off between d, which is the Hamming distance of your code, and r, which is the locality. So you can, for example, try to see what's going on for MDS code. So MDS code, they have locality k because you actually need k other coefficient to recover. And they are known to be MDS, so their Hamming distance is n minus k plus 1. So you can actually put them in this bound and observe that it gives you a tight bound. Okay, so this shows that the bound which is here is actually tight, but of course in this case you have high locality. And so pyramid codes are also a good example that you can fit in this bound, where you can get codes which are like optimal with respect to this bound, but at the same time, so yes, you have optimal repair locality, but you can decide basically if you want to work at a particular regime of R, that gives you a sense of what are the best parameter you can get for the rest of your codes. Okay, so if you are interested in this topic, it's a topic which has many connection with its original engineering problem. So, in fact, the coding problem is harder than what I tried to abstract. So there is the mathematical abstraction, and actually there are a bunch of other things that play a role. So what I have shown in this diagram is that the whole system, you have actually the issue. If you care at designing the whole thing, you have the issue of how you even bring the data into the system, whether you make replica or whether you use erasure-coded data, and then you have the issue of how people access this data. what is written here is that it's actually pretty true still for most actual system, namely that usually I did say that most of the big cloud storage provider are using erasure coded data, but just to be clear, they are also using replication. So the way it works is that they distinguish what they call cold data versus hot data, and cold data is basically data you can archive. So from the moment you can archive it, it makes sense to erasure coding it. For data that is really in access all the time, it doesn't make a lot of sense. So you can think of that in terms of your email, the email you are working with, because it's really urgent to handle them now. It doesn't quite make sense to archive them, so it wouldn't make sense to erasure code them. However, those that you just keep for record, but that you will access like once in a year or once in 5 years, it definitely makes a lot of sense. So, so from a system viewpoint, the picture is actually more subtle than what I have explained. So to wrap up, what are different research areas which are tied up to this topic? Again, it's a topic which is at the intersection of, well, there is a lot of work coming from engineering, and there is a lot of work coming from mathematicians, like normal coding theory, like standard coding theory for communication. So for people who are looking at it from more of an engineering perspective, you will actually ask questions like storage allocation. Where do you actually store your data? You would be asking things like, discussing things like MapReduce job, which are handling how you actually integrate your distributed storage coding strategy into your distributed file system. You may discuss what happens if you use it for data center or if you're using for P2P network or so on and so forth. I guess for the audience of this workshop, the main aspect of interest would be those here. So there is the issue of code design. I do believe that like the standard construction, like meeting those bounds, and actually there have been really many variations of those bounds and further property that people have exploited, which I cannot cover in 1 hour talk. So a lot of work has been done on this topic recently. So I'm going to mention those aspects which I believe are still the most open. And one of them will be code design related to updates and mutable content. So how to design the new generation of this storage code that makes them more friendly for data that may be changing, that may be updated. That I believe is still a topic. It's harder. So it's not that it hasn't been touched, but it has been less studied probably than the other aspect I have mentioned. There are connections with security also, whether you can, for example, do joint coding and security at the same time. And finally, I would mention something, though I don't know much about it. If you ask me what is the area which is related and the most active these days, it's the notion of caching. So I don't know much about caching. I haven't worked so much on this, but I know that this is one of the areas which is still quite active recently on designing code for storage-related type of application. Okay, so I think I have managed to fit my talk in my 1 attributed hour. So I will do a couple of give a couple of references. So of course I will do a bit of self-advertisement, but actually this is something that I wrote quite a few years ago with a collaborator, but somehow my collaborator is a distributed system guy. So I thought we did a good job in trying to give a good picture from the system viewpoint, which was his side, and the mathematical viewpoint, which is my side. And it's actually a fairly unbiased survey. So you can really read about all kinds of different code techniques that had been used. So that's the good thing about it. The bad thing is, of course, it's a bit old. So it doesn't take into account all the latest nuances and latest research topic that people have been looking at on coding for storage. Okay, so I think I will conclude by that, and well, I'll be happy to take any question if you have.
All right, thank you so much, Frederic, for this overview. guess it's open for questions. If anybody has, I saw that one participant, I think Poonam Garg, had raised her hand in between, and I asked if she had a question, and I'm not sure. But anyway, you can ask your question by unmuting yourself or by typing in the chat box.
Hi, Frederick. My name is Lakshmi. Thank you for the interesting talk. Can you maybe tell us a little bit more about mutable content?
Yes, so mutable content is, so as I mentioned, you have this, so what storage like cloud system do at the moment is they differentiate cold and hot data. So hot data is data that people are using. So I'm going to give you an example. Okay, say you are using, what would be a good example? Well, say you are using any, let's say, Office 365, okay? So you are writing a paper with a colleague, and the two of you are writing a document at the same time. And so you have this document which is getting modified. So this example is probably not a great example because a document which is like modified on a day-to-day basis, probably you're not going to be using erasure coding for that. But you could imagine a document that I don't know, you wrote your paper on this shared document and you are not using it for a while, and so it goes for archival. But then somehow you may still want to update it because I don't know, your paper comes back for review. You have to dig it out and you have to start editing it again. So the question would be, okay, so if your paper has been archived using an erasure code, so the question would be of the form like, okay, what are you going to do? Are you going to undo are you going to decode everything, get back the original data and make a replication? Or if you are going to change only a small piece, is it possible to actually keep some of your data encoded and just adjust the part which is changing? So the issue is more like if you think your data is moving a little bit but not so much, how can you, I mean, can you do that in a smart way, or is the only way just redecoding everything, create copies and just work with the copies? It's also, if you wish, the issue of updates. Okay, so if you have, let's say you have you used erasure coding for a big chunk of data, and suddenly you want to change a small piece of that. Are you forced to like? So typically you would do something like, okay, maybe you are going to just compute the difference between the old version and the new version, and then maybe try to just store the difference, or how are you going to combine your keeping track of the update with your erasure coding strategy?
Okay. Thank you, Frederick.
Does that make sense to you?
Yeah. Thank you.
Okay, thanks.
More questions, comments? So, when was your book published? Which year was this?
It's a few years ago. I forgot the exact year. It's already it's already a few years old.
Okay.
And again, I haven't given credit to, I mean, this was really a very, very active area. So as I said, in 1 hour, there is no way anyone can give a really fair overview. But I really feel that most people who work on this topic, if they are fair enough, would say that the regenerating code and the locally repairable code are really the two main classes that people have been looking at. But of course, different groups have looked more into one aspect or another.
Yeah. Okay, I think if there are no further questions, let's thank Professor Federico Gay once again for all these nice
things. Thanks for listening to me for 3 hours. Thank you.
Yeah. And we hope you will also share the slides of this. I think you probably did already.
Yes, I did send already. And this one, I managed no typo, so yeah.
Yeah, I have already uploaded the lecture third slides as well.
Very good. Yes, I just quick with that. So, by the way, yeah,
and hope to meet her in the offline mode sometimes, if possible, in future.
then you get your samosa and chai.
Yes.
Yes, I hope so. Finger crossed.
Yeah. Okay, thank you once again. So let's say we have a break of about 25 minutes, and then we'll resume with the talk of Annalena. See you.
Okay, thank you.
Thank you.
Hello, everybody.
Hi, Anilina.
Works. How are you all doing?
Good.
Very good.
How about you? Yeah. How are you doing, Anilina?
Yes.
No, I just said, how are you doing yourself?
Oh, sorry, I didn't hear that. That didn't make it to me. Thank you. I'm good. I'm good. Yeah, I think, let me see if my slide sharing works. I would quickly like to run back to my kitchen and get a cup of tea, if that's okay.
Yeah, go ahead. We have 10 minutes almost. Yeah.
Perfect. Be right back.
Okay, Kapish and Meena wants to know how the participants will get certificates. So I guess our idea is to send you an e-certificate, but if somebody wants a hard copy, we can also mail a hard copy. Right, Arun? I don't know if it's there. So names and institution correction link not received yet. So are you saying that the names or institution entered in the registration form is wrong? I don't know if Kapish Chandmina is here to ask the question. Maybe he's on a break. We'll discuss it later then. Yeah, you can speak. You can unmute, Kapish, or even have your video. We are on a break, so.
Hello, good afternoon, sir.
Yeah, good afternoon.
Sir, I think I registered 2 times.
Okay.
And exactly I don't remember. I have filled correct or incorrect data.
Okay. We have given everybody a chance, to even edit their responses.
Okay.
So, so you must have gotten some acknowledgement. You can even go back. You can edit your responses and check if your name and institution appears correctly.
Okay, sir. Thank you.
And then if you have multiple registration, maybe you can cancel one of them. Is there any registration fee confirmation notification? If you have paid, you would have gotten some kind of a confirmation from the bank. And when we give you the certificate, we can also give you a receipt of the registration fees. Some people will need it. Arun can probably say more about this, but maybe he's not here at the moment. Arun, are you there? So I think, we should be able to do that.
What's the weather like for you there at the moment?
Well, we usually joke that the weather here is usually hotter and hottest, but it's about 30 degrees.
How many?
Plus or minus 30.
30. Oh my goodness. Yeah. So you don't know the notion of winter.
Well, when it's 25 degrees, we call it winter.
Oh, okay, I see. Yeah. I lived in Florida for a year. It wasn't that bad, but kind of the same idea, yeah.
Occasionally, it may go down to 20 degrees or something like that in the month of January, and people
That's still very cold.
and whatnot. Yeah, Mumbai, the temperature typically is between 25 and 35 all year round.
All year long.
Yeah.
Yeah, wow. I guess most people enjoy that, right? I don't know. I like seasons too, but of course I also get it, like at the end of winter, it's enough. Then I always feel like, oh, I want to live in.
But of course, it's rather humid. Some people like it, some people don't. I mean, some say dry heat is worse.
Really? I thought everybody says moist, humid heat is worse.
Yeah, well, it's
okay. Depends.
If you go to Rajasthan or places like that where there is really very dry heat and temperature goes well beyond 40 degrees, in summer, then
yeah,
you would take humidity, or at least a little bit humidity.
Probably, yeah. True.
Good afternoon, sir.
Good afternoon.
Patil sir is not present at the present now, but he will become within 5 to 6 minutes.
That is fine.
Okay, sir.
We have about 4 minutes, I think. So you will share your slides with us, no? Eventually, Annalena?
Yeah, sure. Shall I just send them to you via email or the group of organizers?
Just send them to me by email, yeah. Me and maybe Sathya. Or you send it to me, I will, yeah. We already have a tab on the workshop webpage where we are putting up slides as and when we receive them from the speakers. We think this will be useful for the participants.
Absolutely, of course. Sure. And for anyone who's interested, I did not put reference in my slides, but I put a little note saying, if you want any reference recommendation, just ask me. Happy to share them.
Even if you add them an extra page of references, that will also be fine.
Yeah, I don't really have a list, so it would just be a lot of effort, I think, to make a list really with all the references.
For the time being, just send them as they are.
Yeah.
Look pretty good to me.
Let me just check if my Wi-Fi router is on, my extender. Fine. Maybe just another remark for everyone listening. I really have to leave it so in an hour, 12 my time. So I will simply finish like 5 minutes before to have time for questions, but as usual.
Yeah, I think we'll start. I think it's time. Yeah, please. You can start.
Perfect. All right. So welcome back to the second part of my introduction to random network coding. Let me just repeat what we're actually trying to do and the last things that we've seen the day before yesterday. So what we want to do is we want to construct codes, so subsets in this Grassmannian space. So we want to construct sets of k-dimensional subvector spaces of fq to the n. And we want to do that with respect to the subspace distance, which is defined as follows for the Grassmannian. So the subspace distance is always 2k minus twice the dimension of the intersection. So basically we want to find good packings in the sense of that, well, many elements in there that intersect in little dimension, small dimension, let's say. Or the dimension that we fix via the subspace distance, the minimum subspace distance that we want to achieve. And one of the first intuitive things, if you know about rank metric codes, that you can do is this lifting operation of rank metric codes. So you take a rank metric code back here, you append an identity in front, take the row space of this matrices, and that will give you such a subspace code in that Grassmannian. And the nice thing is that the minimum rank distance times 2 gives you the minimum subspace distance of this lifted code. So that's a nice thing. And it performs quite well, asymptotically even optimal. However, in the non-asymptotic regime, there's still quite some space for improvement. So that was now the next question, like, how can you do better with this? So the next idea you could come up with is, well, how about we don't, take just this row-reduced echelon form where we have this identity in the first k columns. How about we look at more general possible row echelon forms of subspaces and what can you do there? And for that, two important things that we will work with in the constructions are the identifying vector of a subspace and the Ferris diagram corresponding to a given reduced echelon form or a given subspace. So the identifying vector of a given subspace is the binary vector of length n, so that's also the length of the ambient space that we're in, and weight k, that's the constant dimension, such that, so Hamming weight in this case, okay, Hamming weight k, so there are k1s, okay, and these k1s are exactly in the coordinates where the row-reduced echelon form of the subspace U has the leading ones, or the pivots. All right, so that kind of uniquely identifies this form, the row-reduced echelon form of the subspace. And then inside that shape, that form, the remaining entries that are not fixed by the row-reduced echelon form, they form a Ferris diagram or a Ferris tableau, if you like. The important part that we will now again relate to the rank metric. So here's an example. If we're looking at this subspace here, so the row span of this matrix would be the subspace U, the row-reduced echelon form is exactly this. Now the leading ones, or the pivots, are these guys here, so they're in position 1, 3, and 4. So this is the identifying vector, okay? It's 0 everywhere else, and it has a 1 exactly in these positions 1, 3, and 4. So if I give you any such vector, you can also uniquely create this row-reduced echelon form. You simply don't know what the entries in the yellow part would be, but everything else is already fixed by that identifying vector. Well, and then the rest, that yellow part, is if you take the numbers that you have in the matrix, then you call it a Ferris tableau. And if you simply replace that by dots, for example, because you're just looking at the row-reduced echelon form matrix shape and not a specific a specific given subspace, then everything with that row-reduced echelon form will have non-fixed entries of this form. Okay, so this is the Ferris diagram. The Ferris diagram have lots of other applications or origins in mathematics, okay, which we will not go into detail here, but of course there's lots of interesting things you can do with them. For us, it's simply important that they come from these row-reduced echelon forms of the subspaces that we want to construct. So now, let's just go through this quickly. Again, I'm going to share the slide, so there's more details on here if you want to have a read. But for the talk, I'm just going to go through the ideas on an example basis here. I hope that you see what's happening here. So you can also go the other way around. As I said before, if I give you an identifying vector, you can uniquely construct the corresponding Ferris diagram for any subspace that would have this identifying vector. And we don't care about these free entries there. So it's really just about this shape of the row-reduced echelon form. And how do you do that? Basically, you count the number of ones that you see, because that will give you the constant dimension. So you know, the size of your matrix. Okay, the length is also given by that. So you know that the overall matrix will be of size 3 times 5, if you look at that. Okay, so k equal to 3, n equal to 5. And then you take, every 0 will give you a row in your Ferris diagram. And the row has, a column, and the column has as many dots as there are ones before. Okay, so that 0, you count the ones on the left, there are 2, so that's this column here. That 0 has 3 ones before. So that's, all right, and you can do that for any given identifying vector. And of course, the other way around is even easier, right? If I give you a row-reduced echelon form, you can of course find the Ferris diagram and the identifying vector. Now, for such a given row-reduced echelon form, can we do something similar as what we did before with the lifting construction? And the answer is yes. We can really do more or less exactly the same with this slight extra condition that if we don't have identity and then a square matrix, that would be the Ferris diagram, not square, rectangle. So if we now have something that is not rectangular by the dot shape, then we have this extra condition that whatever we fill in there can only have non-zero entries where these dots are. Okay, so if you make a matrix out of it and you're putting this Ferris diagram on top of the matrix, you only want to have non-zero entries where the dots are. Okay, and if you have some lower left corner with no dots, there have to be zeros in the matrix code that you construct. And these types of codes is what we call Ferris diagram rank metric codes. All right, so this is defined here. So if you're given a Ferris diagram, so some shape with these dots from before, and you're given some row as the dimension of the code, and then d is the minimum distance of the code. So we're now constructing a rank metric code in FQ to the m times L, such that all code words in this code have to have zeros wherever this Ferris diagram doesn't have dots anymore if you put it on top of the matrix. Okay. Then we wanted to form a linear subspace of this matrix space of dimension rho. And the rank distance between any two distinct code words is at least d. So it's really the same as before for rank metric codes. We're just prescribing this Ferris diagram form now for the non-zero entries, which of course makes it more difficult. Sure. However, you can actually do some nice theoretical results here as well. Well, and this is really a generalization of what we've seen before. So it includes the case that if the Ferris diagram is a rectangle of size m by L, then, this Ferris diagram rank metric code would be a classical rank metric code of normal rectangular matrices where everything can be non-zero, possibly. Oops. So one of the nice results, it's not as easy to handle, but it's still a nice result, is if you have a given Ferris diagram and you want to construct a matching rank metric code for this Ferris diagram, then you can, again, find an upper bound on the size of these codes. So very similar to, the singleton type bound for the rank metric, however more tricky because you have this prescribed Ferris diagram shape now. So the bound is as follows. So the cardinality of such a code is at most q to the dimension is this exponent here, the minimum of all the wi, where wi is the number of dots in the Ferris diagram which are not contained in the first I rows and the rightmost d minus 1 minus I columns. And you take the minimum over all i's that are between 0 and d minus 1. Okay, and d is the rank metric, is the minimum rank metric that we want to achieve. So it's nice to have this result. However, it's not, it's not like a straightforward thing that you can plug in numbers and you get a nice number. Okay, you really have to go through this. Okay, how many dots do I have in the last columns? How many do I have in the first rows? And take all these differences there and then find the minimum. However, still, it can give you an idea if, whatever you have already constructed is optimum or not. And there are some constructions for some or many parameter sets where we can actually achieve this bound, and then we call them Ferris diagram MRD codes. So like in the classical MRD setting, maximum rank distance, we now just add this FD in front here. So, this is one of the open questions. We don't have a construction for all parameters, but we have some constructions where we reach this bound, and it's conjectured that this bound holds and is attainable for all parameters. But that is not solved yet, and that is actually one interesting question one could work on, if you're interested in that. So let's see an example. Maybe that makes things clearer again. Let's say our Ferris diagram is of this form. Okay, 3 dots, 1 dot, 1 dot. And now we want to find a Ferris diagram maximum rank distance code over F2 with minimum rank distance 2. Okay, so we're constructing 3 by 3 matrices such that only this Ferris diagram shape is allowed to have non-zero entries. Okay, as you can see, everything non-zero in the code that I've now constructed is really in this shape. If I plug it onto my matrices here. Okay, so basically we could also formulate it the other way around. This 2 by 2 square down here has to be 0 in all code words. All right, and anyway, here is a solution. Okay, there are some techniques how you can get to those solutions in these very specific settings. And again, I can point you to references if you're interested, or you can also find them yourselves, I guess, if you're looking for these keywords. But I'm just going to give you the solution here. So this is one solution. It has 4 elements. It's actually a linear subspace over F2 to the 3 by 3 of dimension 2. So, you can see, if you add this guy to this guy, you get this guy, 2. And that's all you need, basically. The zero matrix doesn't really make much of a difference for the linearity. It has to be there, but yeah, it's not changing the other elements. So this is a linear subspace. It fulfills everything that we wanted to have. And if you count these wi's from here, so what was that? So we want d to be equal to 2. So we have to count for all i's between 0 and 1. I will read the question when I'm done with this. So we have to count the number of dots which are not contained in the first row and nothing ever, or not contained in the nothing rows and the last column. Wait, in the first 0 row and the rightmost is 1 columns. Okay, so that would be 1, 2, exactly. That would be those 2 guys here. If I cut out the last one here, and if I cut off the first row, I get the same result. I also get 2 here. Okay, and that's exactly the dimension of this code. So this is an Ferris diagram MRD code for this given Ferris diagram. Let me see the question in the chat. Okay, that's not for me. Perfect. All right, and now what was the actual point? What we want to do? We want to lift them, similarly to the rectangular rank metric codes where we plug the identity in front and then take the row space. Here we simply plug it into the row-reduced echelon form that this Ferris diagram came from, and look at the row space, and then we get the same result. So this is how we formulated the lifting operation for a Ferris diagram code. But this is probably now more complicated than the way I've now said it. You start with a prescribed row-reduced echelon form that comes together with a Ferris diagram. and you construct a matching code for that Ferris diagram in the rank metric. And then you plug it back into the row-reduced echelon form, look at the row space of these matrices, and that will give you a constant dimension code of the given size that you started with. And again, the nice thing is that if your rank metric code for the Ferris diagram had minimum rank distance D, the lifted version has subspace distance 2D. And the number of elements is the same as the Ferris diagram rank metric code. And that's all you need basically in the end. Okay, perfect. Sure. Now we have this lifted rank metric code for square. We have lifted Ferris diagram rank metric codes. That by itself doesn't do any better yet, but the cool thing is you can now join a bunch of them. And you can join them in a kind of easily checkable, allowed way via these identifying vectors of the row-reduced echelon forms that you have. And that's the result here. So the cool thing is if you have two vector spaces and you want to look at the subspace distance, this is for sure lower bounded by the Hamming distance of the two identifying vectors. And the idea here really is, if you write two reduced row echelon forms on top of each other in a matrix and you want to look at the rank of what they do, or vice versa, you want to look where they intersect. If they're already in reduced row echelon form, all the ones or the pivots in different columns, they can never do any intersection. And that's basically what the identifying vectors tell us. So all the pivots that are in different positions, they will never lead to any intersection of the two subspaces. Hence, we can count them by the Hamming distance. Where do we have differing ones? And at most, the pivots of the two vector spaces that are in the same column, that can lead to some intersection, and hence really what changes the subspace distance of two elements here. So we have that, and if we have two elements from the same type of form, we have a subspace distance is exactly twice the rank distance of these Ferris diagram rank metric codes in the end. And this together then leads to this multi-component lifted Ferris diagram rank metric code construction. So if you want to construct a code with minimum subspace distance 2D in GQKN, we start with a binary block code. Okay, so now we're relating classical Hamming weight and rank metric to subspace codes. I think this is kind of cool. So we're starting with a binary block code of constant Hamming weight K and minimum Hamming distance 2D. That 2D is the same 2D that we want to have as a subspace distance in the end. For each code in there, so these are now the identifying vectors. Okay, they've also been called skeleton code. So these are the identifying vectors that we start with, and for each identifying vector, we construct the corresponding Ferris diagram, the Ferris diagram rank metric code with minimum rank distance D, lift the whole thing again, and then join the whole things, all of these component codes, and that is a final code of minimum subspace distance 2D. Well, then, of course, the cardinality depends on all these separate component codes, how large they are. But of course, you can include, and that's what you will usually do, you can include a lifted rank metric code from the very beginning in there. So basically, you're doing better than before, right? We already said the lifted rank metric codes are pretty good. Now we can simply join some more elements there. So of course, we're a bit better than before. So here's an example. In GQ36, we want to have minimum subspace distance 4. That means, since k is equal to 3, that means they are allowed to intersect pairwise in dimension 1 at most. Okay, so we start with a binary linear code of length 6, constant Hamming weight 3, and distance 4. Here is one option. So that is not unique, okay? You start with 1, and also that is an open question, what exactly would be the best choice here? But here's one, okay? So they all have constant weight 3, and they have Hamming distance 4 to each other. And these are the corresponding row-reduced echelon forms, which then the dots in here correspond to the Ferris diagrams of these reduced echelon forms. Okay, so sure, here the first 3 ones are the normal lifted rank metric code. Here, that one is that one here, that one is that one here, that one is that one here, okay, and then the third guy. Analogously, and of course only the things that are not in the same column as a pivot or on the left in a row of a pivot So only these guys are free to choose. They can be non-zero. Okay, so that's what constitutes the Ferris diagrams. And in this case, for these kind of very small and simple Ferris diagrams, we know optimal code constructions, and they are q to the 6, so that's just the classical MRD code here, q square for this guy here, and then q here. So the union of all these is a subspace code, subspace distance 4 with that many elements, right? And maybe just to clarify again why these identifying vectors can really say something about the subspace distance. So if you look at the first and the second row reduced echelon form, by the pivots, so pivot here in second and third column and here in fourth and fifth column, like these guys can never intersect anywhere. Okay, so for sure these will always have full rank if you look at these 4 rows here. So the only intersection you can have is in the 2 first rows. All right. And similarly, if you look at the second and the third, for example, the only intersection you can have here is in this guy. So in the second row here and the second row here by the pivots. And so on. Okay. So some remarks. As I said, the size of these codes depends on the choice of the identifying vectors, and then if you have an optimal construction for the Ferris diagram in there or not yet. And it is an open question what the best choice for these identifying vector codes is. So that is not really clear. It was conjectured, or still is, that lexicographic codes, so really, starting with the most ones to the left and keeping always the most ones to the left, as many as you can, that this is the best choice. It's kind of a greedy choice. And that those always contain a lifted MRD code in the classical sense. And yeah, sure, that is a good choice, more or less. However, I think many people are pretty convinced that it's not always the best. So it's not always optimal. But yeah, that's an open question. So that's not entirely clear what's the best thing to do here. And there have been some extensions to that. I'm just going to, throw the names at you in case you're interested. You can look them up. So there are some extensions what you can do on this diagram lifting. There are, some interesting things that happen here. All right. So another cool thing, again, that is slightly related to rank metric codes, but yet now really of a different flavor, is how to get from old to new codes. So from old subspace codes together with rank metric codes to new subspace codes. That's the idea here. And one of the main constructions here is called the linkage construction. This goes as follows. So you take 2 subspace codes, both of constant dimension k, but of different lengths, possibly. Anyway, one is of length n1, one is of length n2, and n1 plus n2 has to equal n, so the actual final length that we want to end up with. So you take 2 subspace codes with minimum subspace distance 2d, so also what we want to achieve at the end. And then you take an extra rank metric code of size k by n2, so the same as the second constant dimension code, and that has to be of minimum rank distance d. And then you can do the following. So you take your first subspace code, write it in the first block, write the row reduced echelon of the elements of the subspace code in the first block, and then append behind the rank metric code that you have. So all possible combinations of the basis matrices of the subspace code and then your rank metric code elements. And you take the row space of those matrices, and then you join with the second component code, which simply has a 0 in front, and then the second constant dimension code that you start with here. So basically, this is just, the second constant dimension code itself with a bunch of zeros to make it length n in front. And this block structure together, you can kind of straightforwardly, we will have a quick look at that. The minimum subspace distance and the minimum rank distance, you will also get minimum subspace distance 2d of the whole thing. Okay, so how do we see that? Let's just have a look again. So U1 is always this guy here in the first block of the first component. U2 is that second constant dimension code. That's basically just happening in the second component. And M1 is this rank metric code here in the second block. So if U1 is not equal to U1 prime, okay, so if you have two code words where this first block is not the same, then when what you get is really just by the subspace distance between these two guys by itself, you already have that also. Whatever you put behind, you cannot have more intersection, okay? Hence, you can also not get a different subspace distance. That's the idea. So that just follows from the constant dimension code where U1 and U1 prime is from. Now, when these two guys are equal, then of course the difference is in that rank metric part back here. Okay, so for sure, I mean, if the two first guys are equal, then these rank metric code elements have to be not equal. Otherwise, we would look at the same code word overall. So these guys are not equal. And then now, of course, again, if you look at the intersection, that whole thing is equal to that whole thing. So again, if you write it in a matrix on top of each other, you do Gaussian elimination, what you end up with is exactly, again, the rank of M1 minus M1 prime, and that is, I mean, just the rank distance again. All right, so that's the case where the rank metric helps us. And then the last case is, okay, what if we take one element from the first and one element from the second component? That is even easier, because in this case, you have the extreme case that they cannot intersect at all because of this zero here. So all the pivots of this second type code word are in the second block, whereas here, because you know that U1 is also k-dimensional subvector space, all the pivots are in the first block. And then again, by the Hamming distance of the identifying vectors, the minimum distance is actually 2k, which is for sure greater than 2d. All right, so this is the linkage construction. Let's just have a look at it again. Subspace code appended with rank metric code, and then 0 and another subspace code. Okay, so this works nice, but then of course, already by seeing, this thing here, you see that there is more space that you can do. And also this 0 is not the optimal you could do. So the next generalization of this construction is what many people call the parallel linkage construction. So it's really the same as before. We have the same U1 as before and M1 as before. Now I changed notation a bit. I will change that before I give you the slides. But that's really the same as before. Rank metric code here, subspace code here, the second subspace code also here. But here, instead of the 0, now we take another rank metric code of minimum rank distance d. However, we need one extra condition on this guy. Namely, that all those elements here, they have to have rank at most k minus d. So at least d and at most k minus d. Okay, so that's an extra condition. Otherwise it doesn't work simply. So that again is also a constant dimension code with minimum subspace distance 2d. And the proof, of course, for all the other cases is the same as before. So the only difference now is this guy here. So what difference do we see now? So if we take one of the first type and now a new guy of the second type with this M2 here, you cannot say anymore that all the pivots or all the ones in the identifying vector are in the second block, because now we don't have 0 here anymore. So it really depends on the rank of this guy. So the rank of this guy tells us how many pivots there are if we look at the row reduced echelon form. And hence, now we said that it's at most k minus d, okay? And here's really the trick. If it's at most k minus d, the rank of this matrix, there are at most k minus d ones in the identifying vector in this block. However, there are exactly k at the same time in the other element here. So if you look at the Hamming distance of these identifying vectors again, you have for sure k ones in the first positions, in the first subspace, and then k minus d and most in the other one. So the Hamming distance is at least d. Okay, and that's exactly what we wanted. If the Hamming distance is at least d of the identifying vectors, then also the subspace distance must be at least 2d. All right, but now of course you can ask, sure, we have for rank metric codes with a given minimum rank distance, but now we have this extra condition that we want something that is upper bounded in the rank as well. How can we find those? And here's another very beautiful result that's helpful here. It's called Delsart's theorem. And Delsart's theorem is basically the weight enumerator of an MRD code, of any general MRD code. It tells you exactly how many elements there are of exactly which weight. And of course, you can count all the ones that have weight at most, k minus d. So you can use that to get an exact formula of the maximum amount of elements you can get in there. Then, of course, the size of the final code, again, depends on the choice of the inner subspace codes. Very often you use lifted rank metric or lifted Farad diagram codes for them. And one of the important remarks, I guess, is that variance of the linkage construction, like parallel linkage construction, has then even been generalized, more generalized. These are currently the best constructions known for many parameter sets. So actually, that's a very, very powerful construction that we have here. And there, as I said, there are currently it's a trend to look at these things, I think. So there's a bunch of constructions coming out at the moment, which have similar, yet maybe with tiny differences, ideas in there. So you can split into more than just 2 blocks, for example, or each block can be split again into 2 blocks, kind of like a recursive idea of the same thing again and again. You can add more codes with other prescribed block structure than the one that is given here. So there are several extending results out there that, again, improve by a little bit. Yeah, but this overall idea, I think, is really nice to see. Again, you use the Hamming metric of the identifying vectors and then rank metric codes and all subspace codes, and you put all these building blocks together and you get very powerful new constant dimension codes. So that's really nice. All right, so that was from old to new codes. Now, 2 more classes of codes that I want to show you. And basically, those are, so let's say the 2 from before are really kind of, like from a coding theoretic point of view came up. We already know rank metric codes, what can we do with that, and so on and so on. Now we look at things that are kind of more known from the algebraic mathematical side and how well they fall in, where do they go in the context of subspace codes? So the first thing is spread codes. So this is a spread code itself is a set of elements in the Grassmannian, so a set of k-dimensional subspaces of fq to the n that pairwise intersect only trivially and that cover the whole space fq to the n. And that's a well-known geometrical object, a spread. Just call them spread. But yeah, that, as I said, it's a well-known geometrical object. And again, it has been well known for ages that the cardinality of such a code is exactly q to the n minus 1 divided by q to the k minus 1. And they exist if and only if k divides n. And then this is also an integer number. And the minimum distance, if you translate this, they pairwise intersect only trivially. That means the minimum distance is the most it can get if they never intersect. So that is 2k if we're in the Grassmannian of constant dimension k. And that is optimal, of course. I mean, if you think about, what is the best you can do? Well, we cover the whole space and we don't intersect. There's nothing you can add that wouldn't intersect. As soon as you add something that intersects another code word, you're not at minimum subspace distance 2k anymore. All right, so of course, that by itself makes it, very beautiful objects because we know when they exist and we know how to construct them and we know exactly their coding parameters and even more structure that you can then also use for decoding and things like that. So spreads are really one of the favorite toys for subspace coding, I would say. So here's an example how you construct such spreads always. So we want to construct a spread over F2 in G24, so 2-dimensional subspaces of length 4. But now, instead of looking at this Grassmannian, we're actually going to this Grassmannian down here. So we're looking at the extension field F4, F2 to the 2. And now, and we're dividing both by 2. So now we're looking at elements of dimension 1 and length 2. And that's a pretty simple thing to look at because dimension 1 means really the lines or projectively the points, whatever language you prefer. And there's not much that, can go wrong with intersections if you just look at lines. Like they always just intersect trivially and that's it. So for sure, if we're looking at one-dimensional subspaces, it's very trivial to construct a spread. You simply take all the lines that you have. All right, so we're looking at this guy here. We know that, well, one version of a spread could be this guy here, where my alpha now represents the extension field. Okay, so now, of course, well, yeah, sure, now we've constructed something trivially over an extension field. How do we go back to the thing that we actually wanted to construct? So here's another beautiful thing from Galois theory. If you have an extension field, you can represent it this way, in this polynomial form. That's probably the one that you would usually use, but you can also represent it in matrix form, square matrix form, where you take the companion matrix of this polynomial. So that alpha is a root of some irreducible polynomial. If you take the companion matrix of that, you can also represent the whole extension field as the F2 algebra of this companion matrix. So in this case, the companion matrix is that, because the companion matrix always has like a shifted identity block, which is just this upper row here, and then the two coefficients from the irreducible polynomial that are not of the highest degree, which is, I mean, this is like a full weight polynomial, if you want to look at it that way. So anyway, that's the companion matrix of this polynomial up here. So what you do now is you replace all these elements of the extension field in the polynomial form by the elements of the extension field in the companion matrix form. So 1 becomes the identity matrix, the 0 becomes the 0 matrix, the alpha becomes the companion matrix of alpha. Alpha plus 1 is simply P plus identity then, and that's actually all you need here. So you get that. And because, I mean, this, changing between the different representations of your extension field, they fulfill everything that you want. Yeah, linearity and the linearity does everything for you already in the subspace distance. So before you had no intersection here, except trivially, okay, only in the 0 points. So again, you will have the same when you go to this matrix representation. And well, in this matrix representation, we now have matrices of size 2 by 4, and they're all full rank. So we have a constant dimension code in G24. And that is a spread, okay? And you can do that for any parameters where k divides n. You take both parameters divided by k and take the extension field of degree k here. So that's a very beautiful construction, and it's not the only construction for spreads, but it exists for any parameters that you can do that. So you can always construct these wonderful optimal codes if you want minimum subspace distance 2k. Right, 2k is of course the maximum the subspace distance can be. So you could also say this is corresponds to the maximal error correction capability of these types of codes. Maybe that's not necessarily what you want, but it's nice, right? I mean, depending on the channel that you have, maybe it's an overkill, but it's nice to have these codes. Some other remarks. Well, the thing that you've seen before, as I said, is one way of constructing these codes. You can also construct them as a union of several lifted MRD codes. Okay, so that's also nice. Can be used, their structure can be used again for decoding and encoding and things like that. As an extension, so other works that have been done, and I think there are still some open problems there, but many things have been solved as well, is about partial codes. So in the case that k doesn't divide n, what we define a partial spread code to be is still, you want basically a subspace code of minimum distance 2k. So they don't intersect. You want a bunch of subspaces that don't intersect each other. However, you can be sure by a counting argument that you will not, if k doesn't divide n, you will never reach a spread because there will always be some remaining elements of fq to the n that you haven't hit yet. Okay, so they cannot cover all of fq to the n. But then we would still, we can still define these things. We call them partial spread codes. And then the question still is, what is the largest you can do of these type of codes and how can you construct them? So there are a bunch of results about that as well. All right, and now the last class of codes, which I personally find very beautiful from the algebraic structure. However, There are, again, too many open problems, or maybe not too many. Nicely enough, we have many open problems about them. So they're not really applicable for most cases yet. But I want to show you what orbit codes are and how you can see them as in a parallel way to classical codes, and that they have really nice structure that we would like to exploit more, possibly. So an orbit code is defined as the orbit of some element. So you start with some element in the Grassmannian, and you take a subgroup, and you take the orbit under that subgroup on this element here. All right. And of course, that's just a set of subspaces, so that could be a code. We call that an orbit code. And there are a bunch of names that you can use or not. So if the group is cyclic, we call them cyclic orbit codes. If the group is the Singer cycles generated by a companion matrix of a primitive element, we call them primitive cyclic orbit codes, or other authors cyclic subspace codes. So that's a bit, cyclic orbit codes and cyclic subspace codes are not really the same. Yet if we're talking about primitive groups, so Singer cycles, then they kind of correspond to being the same in the end, more or less. So we like them because they bear a lot of structure coming from the group. So if you have a group with a lot of structure, then the code itself should have a lot of structure. And we also like them because for small parameters, unions of primitive cyclic orbit codes are, again, among the best known constant dimension codes. For small parameters, however, only because these kind of optimization problems that you find there as the packing problems can be translated nicely into linear integer programming problems that come from this orbit structure. And that's why, like, for only small parameter sets, we have found these very good code constructions from that. But that's not feasible anymore as soon as the parameters get larger. But still, it's kind of a motivation to see, right? I mean, for small parameters, we've seen that you can do really well with these types of codes. And now we would like to find, a more structured way how we can also do that for larger parameter sets. So here's an example. Again, we consider G24 and the irreducible element alpha now in 2 to the 4, such that it's a 0 of this irreducible polynomial. And then we consider this map, which I call phi, which goes from the vector space representation to the extension field representation in the following form. Okay, so we take the row vector and bring it into this polynomial form in alpha over here. And then this is an example of an orbit code. Okay, so I take some initial subspace. Now this is the row space of these two vectors here. And I'm applying a subgroup of GL4 on the right. And in this case, as you might already see, there's again a companion matrix of this polynomial over here. So I'm taking this Singer cycle, so the group generated by this element. You can just write it down like this for any type of group. Then you can compute, which are the elements that you get in this vector form. And then you can compute minimum distance, all the things that you like. However, in this very nice case where this is a Singer cycle, you can also write it in the extension field representation again. So if I'm taking then this vector space here, it's a 2-dimensional vector space over F2, so it has 4 elements, and exactly 1 is this guy here, alpha squared plus alpha, that's this guy here. Well, then the sum of the two, and then, of course, the 0 element. And this always corresponds to the multiplication with alpha then, okay? So the companion matrix multiplication in the matrix representation represents to the just multiplication with alpha in the extension field representation. And then hence you can say, okay, all my code words are of this form because I'm taking this initial guy and I'm just multiplying by alpha over and over and over until I have my whole orbit. And I'm starting at 1 again. Okay, so you can simply, say it's all these things plus I, all the exponents of alpha plus I, if you like. So that's an example of an orbit code. And again, one of the nice things is that spreads can be constructed as cyclic orbit codes. So maybe again, another, motivation to see, okay, we already know spreads are great. And they are also a type of orbit code, even a cyclic orbit code. And actually, the thing that we've seen before is an example of such a code. And if you want to write it down theoretically, you can do as follows. So you choose this initial subspace of your orbit as this. So it's alpha to the, and then the cardinality of the spread, alpha to the twice the cardinality of the spread, alpha to the 3 times the cardinality of the spread, and so on, until you get to q to the n-1. And of course, the 0 element also always has to be in there. And if you now take the Singer cycle, as I told you before, you always add basically plus I for each of these guys. So every element of the orbit will be of this form, and then the exponent plus I. And then you can see right away, okay, we will never have an intersection until we actually get to the cardinality of the spread further, and then all the elements will intersect. So we're actually back to the same thing. And before, they never intersected. You can see that by that unique representation as a power in alpha. So you can see, okay, for sure, we're getting something of the right cardinality. We're getting something with no intersection. So we're getting minimum subspace distance 2K. So the only remaining thing is, does this thing actually form a k-dimensional subvector space to start with? And yes, by, again, some more Galois theory in the background, this is always the case. So you can do that. All right, so let's just go back here. What happens here is, I wrote this in this kind of ambiguous form to, that you don't see that's actually alpha to the 0. This is alpha to the 5. This is alpha to the 10. And the 0 element doesn't make any difference. So if you now hit your alpha on it, you get, okay, alpha to the 1, alpha to the 6, alpha to the 11. The next element would be alpha to the 7, alpha to the 12, alpha to the 17, until you get to alpha to the 20, which goes then back to alpha to the 0. Alpha to the, wait, we are in 2 to the 4, 15, sorry. Okay. So you're going back that this guy will then be 1, all right, and this guy will be alpha square plus 1, and this will be alpha square plus alpha plus 1. Anyway, you're ending up in the same orbit. Okay, your orbit is hence shorter actually than the order of this group would be, okay, because the stabilizer is pretty big. So that's right in here. So here's the rewriting of the element from before. It's actually alpha to the I, alpha to the 5 plus I, alpha to the 10 plus I for any I that you like, but you actually just have to go with I from 0 to 5, or to 4, from 0 to 4. So that orbit has 5 elements, and they intersect only trivially, and hence they're a spread again. If you write down these cowords, they actually do look different than the ones that I constructed before with the Desarguin construction. All right. Another last comment about this. Lifted rank metric codes can also be seen as orbit codes, not as cyclic orbit codes, but also as orbit codes, namely as the group here. All right, so the group, this is a subgroup of GLN. If I take identity, and then this guy here are all the matrices from a linear rank metric code. Right, you can see that that's a group. If you take 2 of these, multiply them to each other, you get an additive structure in this block. And if the rank metric code is an additive group, then this guy here is a multiplicative group in GLN. And if you have this group act on identity 0, for example, then you get exactly the non-lifted rank metric code that we've seen before. All right, so again, orbit codes are kind of like the general nice structure. And maybe, as you know, like really the high picture here, it's actually the analogy to linearity in classical block codes. So if you think of classical block codes, you could also say any block code is just a subset of FQ to the n, but then what we really like is subspaces of FQ to the n, because we want linear block codes. And what is a linear block code? It's a little bit more, but it's also an additive subgroup of FQ to the n. And then you could say it's even an orbit of this group on the 0 vector. Like, okay, and this setting here in the subspace setting, orbit codes are the analog in the multiplicative setting. However, we don't have something like the 0 vector, so we need to define these initial vectors of the orbits. But it's an orbit on some given initial space, just now multiplicative groups instead of additive groups. And then you can translate some of the nice properties of linear block codes in the Hamming setting to here. So for example, the minimum Hamming distance for a linear code, and that only works for linearity, is just the minimum weight of all its elements. You don't have to check all the pairs, you actually just have to check the weights of the separate elements. And what is the weight? It's really the distance to the zero vector. And now here for the orbit code, the analog is really exactly the same. You don't have to check all pairwise distances to get to the minimum subspace distance of a code. It's actually enough to check all the distances between the one fixed initial subspace and all other elements of the code word. And by the group structure from the orbit, you get that this implies also the minimum distance for all pairs. So that's another nice thing about orbit codes in general. And linearity in the classical case is also nice because you have a compact representation, namely via a generator matrix, or if you like, a parity check matrix. And orbit codes again have something like that. It's a compact representation via the generator of the group and the init. Much more compact than just looking at, if I give you some type of subspace code, you don't know how to represent it except for writing down all the elements that you have. So these, I think, by itself are really, really nice ideas. However, as I said, there are so many, open questions of what we can actually really do more with this group structure, and we haven't found that many things yet. Some things, yes, but not that many things. All right. Let me see. So I'm almost done with my time. So let me just give you a very, very brief overview of decoding, because again, we actually don't have that many results there yet. But one of the nice things is that we can again just translate everything to the rank metric setting if you're using lifted rank metric codes. All right, so assume you're working with a lifted rank metric code, identity and then elements of a rank metric code. So assume you're sending this guy with M and you're receiving again, a lifted thingy. So IK is the same as before, but then N in the back. By the same thing that we've seen before, the subspace distance between the send guy and the received guy is exactly twice the rank distance of M and N. Okay, so we just get rid of these identity parts. Hence, we can do the whole decoding in the rank metric code. Okay, we're just looking at N, and then we have to find the closest M in the rank metric. Now, of course, that's a specific case if we also receive something of this form that has an identity, a full identity in front. However, similar things are possible if that's not the case. So if your received word has some deletion or deletion insertions, but anyway, you receive something that is of constant dimension k prime, and k prime is less than or equal to k. Or if it's equal to k, it could be that A is not full rank, although the whole thing is full rank being equal to k. So anyway, this A, even if it's in reduced for echelon form, will not be the identity. That's here. Then you can still reform with simple linear algebra the whole thing. The subspace distance of the send and the receive thing is then, you write it in this form, you do Gaussian elimination. What you end up with is twice the rank metric of, A time the original rank metric code word that you have here, where A is not necessarily a full rank, and N, and these guys are fixed, right? You can see them. I mean, you know what K is and you know what K prime is once you received it. So you can decode now your N in this kind of augmented this changed original. That's the original code, and we have to multiply the whole thing by A, and then we decode in there. But it's still then a rank metric decoding problem. And the same thing the other way around. If we receive something where the received dimension is larger than the originally send one, we can again do a little trick. We need to represent, we need to go with the identity of k prime, but we do again Gaussian elimination and so on and so on. So what we get here is the following. We can decode in this code. So this V4 minus V3N comes from some, this is a permutation matrix such that we bring the received word into this form. Okay, so I don't have time to go through the details, but I think it becomes clear. It's really just linear algebra when you read it on the slides, if you like. So that's kind of nice, right? Everything, if we have lifted rank metric codes, we can just go back to what we know for decoding also in the rank metric. since decoding spread codes, since spread codes can be constructed as lifted MID codes, joined like unions of lifted MID codes, you can also do the same thing here. You just have to make an extra step at the beginning, deciding which of these separate components, which of these, different unions, different lifted MRD codes you should decode in. You take, and you can do that by the Hamming distance of the identifying vectors again. So here's a quick example. If that's the spread code in G24 that we've seen before, and we receive something of this form, for example, so three-dimensional thing, we compute the Hamming distance of the identifying vector of this with this component. Yeah, the identifying vector is always 1100 for this component, and it's 0011 for this component. So the Hamming distance to the second component is way too big, because we only want to decode one arrow. Okay, this is too big, so we're definitely decoding in here, and then we can use the same from before, the rank metric decoder idea. Okay, so we get that we would decode to identity in this case, because that's the minimum distance that we find. And the second idea is you can use the actual properties of the spread code, that every element of FQ to the n appears in exactly one code word, every non-zero element. So you can do something like a majority vote decoder. All right, you get a receive word, and you simply go through all elements of the vector space. In this case, we have 2 to the 3 minus 1, so we kick out the 0. So we have 7 elements in this receive vector space, same example from before. And we're just checking, okay, which code word is it in? And then we take the majority vote for whatever we have in the end. So the first row says, okay, I'm actually in this code word. The second row says I'm in this code word. Third row says in this word, and then we take all the linear combinations. And what we get in the end is, well, the majority vote is clearly, if we can uniquely decode, it's also a unique vote here. And we're going to decode to that majority vote here. So that's kind of, I think, theoretically really easy to explain. However, that only works well if K and Q are small, because you basically have to go through Q to the K more or less elements here and ask them for their vote. With some smart things, you can speed it up a bit, but not too much. So, and then the last thing is orbit codes. Again, the nice thing is it's kind of analog to the linearity for block codes, so we can also do something analogous to syndrome decoding, more or less. And we have like the theory for it, but we have no practical instance at all yet. That would really depend on a nice group. If anyone finds a nice group that we can do syndrome decoding efficiently for orbit codes, that would be fantastic. Okay, so that is really like on my big list of things that I would really like to find, but I haven't found it yet. But let me just, as the last thing, quickly say like how it would go. Well, if you have an orbit code of the form U times G is a group, use an initial vector space of your orbit, then you can partition the whole Gaussian into orbits under this G. Okay, so let's say that the first orbit is our G, and then you have a bunch of other orbits, and you can define some initial subspace for each of these. You actually now want to say we choose specific ones, called the coset leader or orbit leaders. Specifically, we choose those that have the minimal subspace distance to the initial subspace of the code, of the orbit of our code. All right, so that would be, again, the idea of the coset leaders in syndrome decoding are the lowest Hamming weight code words, because they have the least distance to the 0 element. And then for a receive word, we need to first find the orbit that it's on, and then the element A such that, the initial point on that orbit times A is the receive word. And then again, by all that group structure, that the closest corresponding code word is U times A, so that A is exactly the important thing here. Okay, you just change from one orbit to the other, but then the point on the orbit is given by that. All right, cool. So here is another proof idea if you want to have a look. And let me just summarize, since I'm slightly late, but that's okay. So I gave you an overview, of where random network coding comes from this non-coherent single source multicast communication channel. We do want the inner nodes, we allow the inner nodes to do random linear combinations, And hence we needed to set up like some coding space that is invariant under linear combinations, and we needed a new metric to decode with. And that was exactly going to the Grassmannian or the projective geometry and using the subspace distance. The error types are very different. There are now dimension increases or decreases. And so I still stick to insertions and deletions, but ascensions and descensions was also a nice suggestion that you could call them. And then I gave you an overview of a bunch of constructions that we have and the few decoding algorithms that we have for these. And the open problems, there are a bunch of them. So there are still gaps between the upper bounds and the constructions that we have. We still have no efficient decoder for orbit codes. When would it be useful to use non-constant dimension codes? Also a good question. When would it make sense to actually not look at the Grassmannian, but allow different type of dimension for the code words? If there is such a setting, there are already some theoretical results about constructions, coding algorithms yet. So again, lots of space there. And then another nice thing that's really like going into another direction, but that I wanted to say is there might be other error models that you can look at. So for example, there is a model set up where you can correct on a symbol level and not only this dimensional level, because actually we're like throwing away a lot of information if we're kind of saying like one symbol error in a vector makes this whole vector kind of erroneous. So there's no difference in if one vector has one symbol error or 10 symbol errors. In the dimensional problem, in the end, those are modeled the same. So isn't there a better model that you can actually really correct these symbols, although you have the linear operations in the end? And there are a bunch of open questions there as well. It really gets a lot more difficult if you think about that. So sorry for going some minutes over my time, but I thank you for being here and your attention. And of course, I still have like very few minutes for questions if there are any, or, contact me via email. I'm also happy to answer that.
Okay, thank you so much. Thank you for this very nice talk. It's very nice. I think maybe we can take some quick questions. I know she has to go, but if there are questions, just
Sure.
Unmute and ask, type in the chat box. Yeah. I don't see any questions. I think you should be able to make it to your next meeting in time. So
perfect.
But I'm sure I think the people can write to you if they have.
Absolutely, exactly. And I will show the slides.
And you will send us the slides so we can also have a closer look at it. Thank you so much once again. We really appreciate you taking time and giving this very nice talks on random network coding.
I was happy to do those. Thank you for asking me. So,
Okay.
I wish you all the best and a good end of the workshop today.
Thank you.
Thank you. I'm sorry I cannot join, but all right.
Okay, bye.
Bye, everybody.
Bye. Okay, so we have a break now. I think about 27 minutes or so, and we will resume at 5 o'clock. Thank you.
Sir, can I speak? So you were asking about certificate of participation.
Right. Somebody had a question, so I answered the best I could in your absence.
Yes, sir. So I just have prepared one Google form asking two questions to them. One, their name they want on their certificate, and institute they are affiliated to.
Okay, fine. That's very good. Then we will only send it to those who ask for certificates, right?
Yes, sir. Yes,
and paid the fees.
Yes, sir.
Okay.
Who will be paying also? Because some of the foreign participants might have not paid, so they can try once again in our Google Pay.
Yeah.
Our SBI Collect link.
Yeah. Yeah, if somebody has a problem with payment, just write to us and we will try to answer you individually.
Yes.
I know that people abroad had some issues with SBI Collect.
Yes, sir.
I don't think anybody in India had a serious issue in making a payment. But yeah, if you want to pay and you have had problems, just let us know and we will try to answer the best.
Okay. Yes. I think Priti Jain has some problem. Priti Jain want to talk?
Nijani, you have a question or comment? Yeah, she asked if there is a registration fee confirmation, and I said to her that we can send a receipt maybe.
Yeah, invoice we can send, sir. So along with certificate of participation, we will send invoice also.
Yeah, okay. They would need some proof that they made a payment to get a reimbursement
Yes,
or what.
Yes.
Quite understandable.
Yeah. To not to all participants who have paid, we send them invoice, their certificate and receipt.
Yeah. Okay. So let's make the most of our break and then come back in 25 minutes. Anything more you want to add, Arun? Yes. No.
Yes. You are, I think, things are breaking from your side.
Oh, my voice is breaking?
Yes. And little delay.
Oh. Okay. All right. Anyway, then let me quit for now, and then I'll join back later. Maybe I will.
Okay.
If Pawan wants to know if we'll send recorded video, we will try, Pawan. I mean, I don't, as I said before, I don't promise, but we may try to do that if the speakers permit us. Yeah, I mean, recording video, that it has nothing to do with payment. If the speaker permit us, we will give links to recorded video on the workshop web page, so anybody should be able to view them. But some procedure has to happen before that. So I hope I have answered. Hi, Samrit. I guess you're muted.
Hi, sorry. I was muted and didn't realize.
Don't worry. Okay. So I see that your slides are already, looks like a tablet, no?
Yeah, that's right. That's right. You can hear me loud enough, right? The volume.
Yeah.
It's okay.
Yeah, it's okay to me.
Okay, great.
We have a couple of minutes, so we'll just wait for people to.
Okay, sure.
Okay. Yeah, I think it is time. So people can begin. So Samrit will give his second talk. It's been a while since he has spoken. He spoke on the first day, and he will speak on the last day on a very interesting topic. Samrit, you can begin whenever you're ready.
Okay, sure. Thank you. Okay, so maybe before I begin, I would like to say that today's talk, I would like to keep it as interactive as possible. So if at any point anybody has questions, please feel free to either post them in the chat or to speak. So, okay, so I'm going to actually begin with a performance that is made by two mathematicians. Okay, so I want to begin by explaining a certain card trick and then look at the mathematics behind it and then relate that to some topics in this workshop. So here is what happens. So there is a performer. He has a deck of cards, and what he does, he goes onto stage. There is a huge audience. Now, a few people are not convinced that this is a valid trick. So people are allowed to borrow this deck. And each person who borrows it is allowed to give the deck a straight cut. What do I mean by straight cut? Simply split it into two piles and then interchange the two piles. Okay, so a straight cut. So any number of people who wish to may give the deck of cards a straight cut. And once people are convinced that they have had what they want to do with the deck, so 5 people draw cards off the top of the deck. And the performer announces, those of you that have red cards, please step forward. So once this happens, the performer correctly guesses all the cards of all the 5 people. Okay, so I hope that this is clear. Any number of cards are allowed, and once 5 people draw 5 cards off the top of the deck, and so they come forward with those who have red, just simply raise their hand, and all the 5 cards are guessed. So maybe let me say that by red cards, so there are 4 suits: diamonds, hearts, spades, and clubs. So the hearts and diamonds are red, so those are the red cards, whereas the clubs and spades, those will be considered black cards. All right, so maybe I would like to say at the outset that there isn't really any magic here. It doesn't use any of the typical magical devices such as maybe sleight of hand or misdirection, and it's only mathematics here. So let's begin with a few preliminary observations. So here is the first observation. No matter how many times the deck is cut, the final configuration that the cards can have. So let's say that there were n cards in the deck. I claim that the total number of configurations possible after any number of cuts is exactly n. The reason being that the cyclic order of the cards does not change after any cuts. For instance, if you think of the deck, consider the following experiment. Suppose we take 2 cards off the top and put it at the bottom. Now, instead of that, if I take 1 card at a time and put 2 cards below one by one, it's going to result in exactly the same configuration. So any cut of k cards above going below corresponds to simply taking k cards one by one and putting it at the bottom of the deck. So the number of final configurations of the deck equals the number of cards in the deck. The cyclic order is always preserved throughout these cuts. And that's going to be important. Now here is another observation. So which of you have red cards? This question can be answered in 32 different ways because, the red people are some subset of those 5 people. And that could be the empty subset, or all of them could have red cards. There are possibilities. So maybe it makes sense to do this trick with 32 cards. And the idea is going to be that somehow the cards are arranged in a clever way such that after knowing the colors of those 5 successive cards, one is able to guess precisely what the cards are. And so by guess, I mean that the performer guesses the suit as well as the rank. For instance, 5 of spades or 7 of diamonds and so on. And it definitely must be the case that at any point, if you take any consecutive set of 5 cards, those color patterns must be unique. Okay, so that's what we want to have. Now, okay, so let's assume for simplicity that that we do it with a smaller number. So let's say that there are 8 cards in the deck and there are only 3 participants. Now, if you ask for the people with red cards to step forward, then there are 8 possible answers. So the question is, can we find a sequence of length 8 such that each consecutive string of 3 colors occurs exactly once? Okay, because at every consecutive set of 3, we want the color patterns to all be distinct. So it turns out that in this particular case, one can certainly do that. So if one looks at these patterns starting from the beginning, so one has BBB, then one has BBR, and so on, until finally one has RBB. The last one comes by looping around. Okay, so one can easily check that for this particular sequence, you can have each successive sequence of 3 gives you all the possible strings with these 2 letters. So that's the sequence that we have. Now here is one possible way to arrange these cards. We put in some 3 black cards, then a red card, then a black, and 3 more reds, corresponding to this sequence, BBB, RB, RRR. Okay, so more generally, what we want to do, so let us say, so here we had a B and an R, but let's say more generally that we have a finite set of cardinality K. Then at the Brown sequence with window length n over that set S is a K to the n tuple. So each of these xi's come from S, but if you look at any n successive xi's, then all these possible n successive xi's will give you all possible n tuples. Okay, each n tuple occurs precisely once. Of course, here we take indices modulo n, and xk, where k is greater than k to the n, will wrap around. Okay, so for instance, the previous sequence, we could say if S is 0, 1, then this was the sequence that we had. Okay, so if there is, so if I take S equals 0, 1, and if there is the Brown sequence of window length n, so maybe 5 in this case, then you can perform the trick with 2 to the 5 cards. So one can actually prove that given any alphabet of size k, so any set of size k and any window length n, one can construct the Brown sequence corresponding to these parameters. So one way to do that is using graphs, but I'm going to skip through this for now. And so one can do it in principle by looking at Eulerian circuits in a suitable directed graph. But I'll come back to this later. I'll go to another way of constructing these sequences, and maybe I'll come back to this later on if there is time. So I'll just skip this for now. But let me just say that given any k and n, these sequences do exist. So for instance, for n equals 5, if we manage to find the Brown sequence, so this would be a sequence of length 32, where each successive 5-bit strings, each of these are all distinct, and they give you all the 2 to the 5, which is 32 strings of zeros and ones. So one way to do this might have been to arrange the cards in the following order. It's seemingly random, just that we think of the zeros as black and the 1 as red. Okay, so this could be one way to do the trick. But perhaps this is not a very satisfying way because we've proved the existence, but we don't still quite understand what the pattern is in the cards here. And one still has the task, the laborious task of memorizing this sequence of cards. So for this particular sequence, so many patterns are, there are only 32 distinct patterns possible, and these are all of them. So in principle, if one has an amazing memory, one could simply memorize all of these and perform the trick. And it turns out that there is a huge number of the Brown sequences. For instance, for n equals 5, and in the binary case, one has 2048 such sequences. It would be a pity if there were so many sequences, but not even one nice sequence that one could easily memorize. So that's going to be our objective next. So by the way, one way to prove this theorem would be to use the best theorem in mathematics. Okay, which is literally the best theorem. Well, it's named after the Brown, Ehrenfest, Smith, and Tucht. So anyway, so that's probably a slight digression. So let's look at an elegant way to perform this trick. So here is the idea. So we have 32 cards in the deck. The idea is going to be as follows. To each card, we associate a unique 5-bit string of zeros and ones. How shall we do that? Well, we already think of the red as 1 and we think of the black as zeros. And let's go one step further and say that clubs and diamonds have the second bit 0, whereas spades and hearts have 1. Okay, so, well, this is one way of doing it. You could possibly pick another pattern. But nevertheless, the first bit still indicates the color of the card. The first bit being 1 means that this is red, otherwise it's black. And since there are 32, so let's take all the cards in these 4 suits, but with numbers going from, well, with the ranks going from ace to 8. And here we simply use the binary representation of the number. So for instance, we think of ace as a 1. So in binary, in a 3-bit binary, that's simply 0, 0, 1. So 2 would be 0, 1, 0, and so on until we reach 7, which is 1, 1, 1. And 8 will simply be 0, 0, 0. 8 should technically be 1, 0, 0, 0, but let's say 0, 0, 0. We want to represent everything using 3 bits. So now for each of these 32 cards, clubs, spade, diamonds, and hearts, ace through 8, we have a 5-digit string. Okay, so for each card, this is what we do. First, we indicate the suit. So for instance, ace of spade, well, spade is 0, 1, and ace is 0, 0, 1. So this should be 0, 1, 0, 0, 1. Okay, and so on. So for instance, 6 of hearts, hearts is 1, 1, and 6 is 1, 1, 0 in binary. So that's it. There is just one more example. So, well, diamonds is 1, 0. And 8 is 0, 0, 0. So 1, 0, 0, 0, 0. So what we've done is represent each card by a unique 5-digit string, each of these 32 cards. And how do we proceed from here? Well, the Brown sequence that we picked here is actually very special. So the way it is constructed, these successive 5-bit windows, say the first 5 bits, the next 5 bits, and so on, they are actually very closely related. We have chosen as simple a rule as possible to get the successive strings. Namely, we use a feedback shift register. So how does that work? So if you have S1, S2 up to, well, SI, so a given string, if it's SI, SI plus 1 up to SI plus 4, then the next string, you simply omit the first digit, you keep these as they are, and you add a new bit by using this feedback shift register. So the new bit, SI plus 5, is simply SI plus SI plus 2. Okay, so this would give us a sequence. So we know, given any 5-bit string, how to get the next 5-bit string using this rule. So the one place where we make an exception is between, so technically, if you go to 1, 0, 0, 0, 0 and you apply this rule, you will go here. So it turns out that the period of this feedback shift register is 31. But we want it to work for 32 cards, which is why we artificially insert this extra 5-bit pattern there. So the 0, 0, 0, 0, 0 is inserted between these two strings. All right, so why does this work? So the card arrangement is done according to this rule. So for instance, what this rule gives us is a new card. So given any card, it's a 5-bit string. I can apply this rule, SI plus 5 is SI plus 2 plus SI, and get a new card. So what you do is the card that you get from a given card, you put it behind that card. Okay, and like this, you arrange all the cards in a sequence. So for instance, if you have an ace of spade, that's 0, 1, 0, 0, 1. And this, the feedback shift register will take it to 1, 0, 0, 1, 0, which is a 2 of diamonds. And so the 2 of diamonds comes behind the ace of spade. Okay, so similarly, if you have a 2 of diamonds, so what's behind the 2 of diamonds? Well, this is 1, 0, 0, 1, 0. It goes to 0, 0, 1, 0, 1. And that is simply a 5 of clubs. Okay, so what this has done is given a single card in the deck, I can arrange the whole deck by placing all the cards using this feedback shift register. So if I know a single card, then I can guess all the consecutive cards in the deck. But how do I get that first card? So these are the card patterns possible, depending on where those 5 cards, the 5 successive cards are taken out. But it turns out that we really don't need to remember anything else here. So here is the idea. So this is how the trick works. So those 5 cards that are taken in sequence, so suppose the people say that they have, say 2 people have red cards, so it's red, black, black, red, and black. So first the performer converts this to binary. So remember that red is 1 and black is 0. So that simply corresponds to 1, 0, 0, 1, 0. Now the way the sequence is constructed, the bits corresponding to a certain card, the successive bits actually give you the colors of the cards coming later on. For instance, we know that the card after a 1, 0, 0, 1, 0, its first bit is going to be a 0. And that means that the card behind this card is going to be black. And the next card is going to be black as well, and then a red, and then a black card. So basically, the way the cards have been arranged, this simply means that the first card is a 2 of diamonds, because that's what the sequence corresponds to. So the 10 is a diamond, and the 0, 1, 0 is a 2. And one can use this to guess the remaining cards. Simply put this through the feedback shift register. Okay, so you have 1, 0, 0, 1, 0, then 0, 0, 1, 0, 1, and so on.
Sir, how we write this? Please explain.
Could you please, I couldn't hear that. Could you please repeat your question?
Sir, please repeat this pattern. How we write this?
How do we write this pattern? Okay, so let me come back to that. So, well, I guess this is clear. This is the way in which we encoded the cards. So the 10 gives you the diamond and the 0, 1, 0 gives you the 2. Now, how do we get the next card? Well, we use the feedback shift register that says that this should be, well, 0, 0, 1, 0, and we add the first and the third bits, so 1. So that's how we get the next. It's simply 0, 0, 1, 0, 1. Okay, I hope it makes sense. And you use the same rule to get successive cards. So you apply it again, you'll have 0, 1, 0, 1, 1. And then 1, 0, 1, 1, 0. Only one bit is new. All the other bits, you simply shift it left and add one new bit. Okay, I hope that answers your question.
Yes, sir.
Okay, and the moment you have these cards, well, it's a matter of converting, you know the binary representation and you need to convert it to the suits. So that's a 2 of diamonds, a 5 of clubs, a 3 of spade, and a 6 of diamonds, and well, a 4 of spade. Okay, so this is how this is performed in practice. So I hope that the idea of this trick is clear. Basically, all that is underlying this magic trick is a feedback shift register. Okay, so maybe let me say a few words about the person who actually came up with this trick. So it was Charles T. Jordan, who was a chicken farmer from California. So So he was quite a bright guy, but he actually came up with many card tricks by himself. And he was too shy to perform them. So what he did was that he invented new tricks and he sold them at a suitable price. And that was how he made money. I mean, he did many other things as well. He also built radios and so on. But as far as this particular trick was concerned, it came under the name Coloria. That's what he called his trick. Apparently, when in his version of the trick, he would ask for 6 consecutive cards and then guess all the cards. So he had not mathematically optimized it. That happened a bit later, and the idea of using feedback shift registers to perform this trick, although they don't explicitly state it, is due to Percy Diaconis and Graham. Okay, Percy Diaconis was actually a professional magician before he became a mathematician. He's a professor at Stanford, and Graham, he's a very famous mathematician himself. So this particular presentation of the trick is from the book that they co-authored called Magical Mathematics. It's highly recommended. It makes for light and easy reading. And in fact, they don't even talk about primitive polynomials and so on there. It's very accessible, I would say. They don't bring in any complicated algebra and so on. So they claim to have performed this trick at all kinds of bars and places and so on. I will say that maybe initially when you first see how the trick works, maybe it's it takes some practice to remember the binary encodings and so on, but it can be done. It's not really difficult once. With some practice, this can be performed quite well. Okay, so let's bring in some algebra here and let's look a bit deeper at this trick and see what makes it click. So maybe a quick recap. For each prime power q, there is a unique finite field with q elements, okay, and we'll denote that by g of q. And for each positive integer n, there is a unique extension of degree n of this field, of course, up to isomorphism, and that's fqn. That extension is Galois, and the Galois group is cyclic of order n. And one of the nice things about finite fields is that the multiplicative group is cyclic. So recall that a generator of the cyclic group is called a primitive element, while the minimal polynomial over fq of a generator of fqn will be called a primitive polynomial. That is going to be a polynomial of degree n, and it will be irreducible over fq. Okay, so for our purposes, this is really the important polynomial. So we had si plus phi is si plus 2. So it turns out that the reason this trick works and the reason that feedback shift register has a large period is that this polynomial is primitive. It's actually not difficult to prove that this polynomial is primitive. So in this particular case, okay, so I claim that it's irreducible. So a polynomial of degree 5, to say that it's irreducible, it suffices to say that there is some irreducible factor of degree less than or equal to 2. That's because if you write f as gh, then g and h can't have both degrees at least 3. One of them has to have degree less than or equal to 2 and hence be divisible by an irreducible polynomial of degree at most 2. And so there are only 3 polynomials that we need to check since we are over g of 2. And this can easily be verified. Okay, so 0 and 1, there are no roots in the base field, so you simply need to check divisibility by this polynomial. So take a root of this and plug it in, and you'll see that it does not satisfy that polynomial. So this polynomial is certainly irreducible. And luckily for us, we know that whatever order it has should divide q to the m minus 1. Okay, in this case, it turns out that q to the m minus 1 is a prime number. So e must be either 1 or 31. So e cannot possibly be 1. This is a polynomial of degree 5. So in fact, for this polynomial, its order is simply 31. And that automatically makes it a primitive polynomial. And this is why it gives a feedback shift register with period 31. Okay, so recall that a feedback shift register is simply given by a recurrence, where each Si plus n is a linear combination of Si through Si plus n minus 1 with these scalars Ci which come from Fq. And one can look at the infinite sequence generated by the feedback shift register. This is always eventually periodic and is in fact periodic if the C0 is non-zero. And then we can say that this feedback shift register is primitive if that infinite sequence has the maximum possible period provided you start with a non-zero initial state. I guess that Sartaj already spoke about some of these, so this would just be a quick recap of that. The point is that this feedback shift register is primitive if and only if it's characteristic polynomial, which you define in terms of the coefficients. That polynomial is primitive. Okay, so maybe our running example here is this feedback shift register. And the reason that that is primitive is that this polynomial x to the 5 plus x squared plus 1 is primitive over F2. Okay, so how many primitive linear recurrences of order n are there? Well, I guess I kind of already answered this, and maybe even Sartaj spoke about it. We simply need to count the number of generators of Fqn and then divide out by n. Okay, the number of generators is phi of q to the n minus 1, where phi is the Euler totient. And since each polynomial of degree, primitive polynomial of degree n has n of these generators, you simply need to divide out to get this number. Now here is an important generalization that goes back to Niederreiter. Okay, so Niederreiter, his idea was to, instead of considering scalars, his idea was to consider of primitivity for these vector recurrences. Namely, for any non-zero choice of initial state, you get the maximum possible period. And the problem here is, can we determine the number of primitive vector recurrences of order n over Fqm? So we're thinking of it as Fqm because each of these SIs is an m tuple. Okay, so this was a problem that was open for a while, but we'll come back to this in a bit. So closely related to these vector recurrences are what are called splitting subspaces. So if m and n are positive integers and you take an element of Fq to the mn, call it alpha, then an m-dimensional, so you can think of Fq to the mn as a vector space over Fq of dimension mn. And an m-dimensional subspace W will say that it is alpha splitting if you can write Fq to the mn as a direct sum of alpha to the I times W as I goes from 0 to n minus 1. So we need this direct sum decomposition. Any m-dimensional subspace for which this happens will be called alpha splitting. So these splitting subspaces were also introduced by Niederreiter. And this was the question that he posed. So suppose I have an element alpha that generates the extension Fq to the mn over Fq. In other words, alpha satisfies an irreducible polynomial of degree mn over Fq. Then what is the number of alpha splitting subspaces of Fq to the mn of dimension m? Okay, so this is closely related to some combinatorics in the general linear group. So let me talk about that. I guess Sartaj also briefly spoke about this yesterday. So the general linear group over a finite field is a finite group and has this well-known order. In fact, in the case where Q is a prime, this goes back all the way to Galois. This is a result of Galois that its size is given by this simple product. So the question is, what is the maximum possible order that a matrix, a non-singular matrix over FQ can have? And how many elements are there of this order in this group? So let's call, the maximum possible order is in fact Q to the n minus 1. And an element of this order will be called a Singer cycle. Okay, so there are elements of the maximum possible order in the general linear group. As for the number of Singer cycles, well, one can show that a matrix is a Singer cycle if and only if its characteristic polynomial is a primitive polynomial. So one way to count the number of Singer cycles would be to count the number of primitive polynomials. Okay, so that is the factor in blue here, this phi of Q to the n minus 1 by n, that is the number of primitive polynomials of degree n. And then for each primitive polynomial, look at all the matrices which have this given primitive polynomial as their characteristic polynomial. That is the second factor. So it turns out that that is actually also not very difficult to see. In fact, the reason that there are so many matrices with a given primitive polynomial is that if you fix a primitive polynomial of degree n, then all the matrices with this characteristic polynomial, they form a single conjugacy class. And so you would get the size of this conjugacy class by dividing the order of the group by the size of the centralizer in GLM for this particular matrix. But a matrix with an irreducible characteristic polynomial necessarily corresponds to a cyclic linear transformation. So any matrix commuting with that matrix is a polynomial in that matrix. And modulo its minimal polynomial, they are Q to the n polynomials. But of all these polynomials, we only want the non-singular one. So you need to throw out the zero polynomial, and then you get that the centralizer size is Q to the n minus 1. Okay, so this is the number of Singer cycles. Okay, so closely related to the vector recurrences are what are called MN block companion matrices. So what's an MN block companion matrix? It's an Mn by Mn matrix over Fq, and it has this block form. So earlier we had, the way it differs from a usual companion matrix is that now all these zeros are block elements. All these blocks, each of these blocks here is an M by M matrix. Instead of the ones which you had below the main diagonal, you simply have identity matrices of size n. And the last block column, you have these M by M matrices, the CIs. Okay, and the reason that these are significant is that these are, so I guess Sartaj spoke about the state transition matrix for a feedback shift register. So these are precisely the state transition matrices for the sigma LFSR or the vector recurrences. So the properties of the sigma LFSR would depend on the combinatorial properties of such a matrix. So for instance, if such a matrix is a Singer cycle, then we would obtain in the sense that this has the maximum possible order in the corresponding group, then this would correspond to a sigma LFSR of the maximum possible period. Okay, and the problem here again is, can I determine the number of block companion Singer cycles over FQ? So let's come back to recall that we had these splitting subspaces, and so let's denote by sigma mn alpha the number of m-dimensional alpha splitting subspaces over Fq to the mn. So the problem was to determine this sigma mn alpha given values of m and n, provided this alpha generates the extension of fq to the mn over fq. So, motivated by the work of these three mathematicians, we were led to a quantitative formulation of this question. So, we had a conjectural answer to this sigma mn alpha. So if alpha generates the extension of fq to the mn over fq, then sigma mn alpha is given by this formula. So it turns out that one could formulate a bunch of other conjectures that are closely related to this question. Okay, so one is the primitive vector recurrence conjecture. So that is a question that I asked a little while ago. So how many primitive vector recurrences of order n are there over fqn? Okay, so the conjecture was that it is given by this product formula. So if you see the first term in the product, that is simply the number of primitive polynomials of degree mn, pi of q to the mn minus 1 upon mn. And this was already conjectured by Zheng, Han, and He for the case q equals 2. And the generalization to the query case is due to Sudhir Sartaj and Meena Kumari. So, okay, so there is also this block companion single cycle conjecture. So the number of mn block companion single cycles over fq is also given by this formula. Okay, so this is because the block companion single cycles are the state transition matrices of these primitive vector recurrences. So that's the connection between these two conjectures. And then the primitive fiber conjecture. So if you're given, one can look at a given primitive polynomial of degree mn and ask how many mn block companion single cycles have this f as its characteristic polynomial. Okay, and the conjecture was that it's given by this product. And one can ask a slightly more general question. Forget primitive. Suppose we just take an irreducible polynomial of degree mn. Then how many mn block companion matrices have this given polynomial f as their characteristic polynomial? And the guess was that it should be the same as in the primitive case. And the hierarchy between all of these conjectures was that, okay, so there is another pointed splitting subspace conjecture, which I haven't stated, but it is equivalent to this splitting subspace conjecture. The splitting subspace conjecture is equivalent to this irreducible fiber conjecture, that's number 4 here. The irreducible fiber conjecture implies the primitive fiber conjecture because primitive polynomials are a subset of the irreducible ones. The primitive fiber conjecture implies the block companion single cycle conjecture. Okay, the number of block companion single cycles, mn block companion single cycles. And that is equivalent, that conjecture is equivalent to the primitive vector recurrence conjecture. So, after remaining open for a while, this problem was finally settled by Chen and Singh. They showed that the splitting subspace conjecture is true. That is, whenever alpha generates the extension of fq to the mn over fq, then the number of m-dimensional alpha splitting subspaces is indeed given by this product formula. Now, I'd like to say here that the proof that they gave was a heavily involved proof and involved a lot of computation. Okay, so it was perhaps a tour de force approach, but maybe here is a tiny excerpt to give you an idea of the kind of calculations that were involved in the paper. There were many pages of calculations, and this is a half a page from their paper. So although the conjecture was settled, it was, from a conceptual point of view, it was not so satisfying. And for that reason, we eventually managed to come up with a slightly more a proof that maybe involves much less calculation. So this, I should say, is joint work with Akansha Arora and Ainiti Venkateswarlu. So there was a brief proof sketch here, but maybe in the interest of time. So what the idea was to prove directly the irreducible fiber conjecture. So I'm actually going to skip this for now and move on. So we managed to give a proof for this irreducible fiber conjecture. And since the irreducible fiber conjecture is equivalent to the splitting subspace conjecture, so this was an alternate proof of that result of Chen and Singh. Okay, so with the splitting subspaces under our belt, we can safely generalize. So suppose we have an mn dimensional vector space over FQ, and suppose that you have a linear transformation T from V to P. So let's say that an m dimensional subspace W of V is T splitting if I can write V as a direct sum of W, TW and so on up to T to the n minus 1 times W. And let sigma m and T denote the number of m-dimensional T-splitting subspaces. Now this is a more general problem than the alpha splitting subspaces problem, because there we are in the situation where V is simply Fq to the Mn, and you can think of multiplication. So multiplication by an element of Fq to the Mn is in fact a linear map, is an FQ linear map. So this problem generalizes that problem, where if you take T to be the multiplication by alpha map. And here is the basic enumeration problem here. Can I find some nice expression for this sigma mn T? Okay, I would like to say here that this problem is still open. It remains open, and barring a few special cases, for the majority of cases, there is no known nice expression for this particular quantity. Maybe one observation that I could make here is that this number, the number of m-dimensional T-splitting subspaces, actually is invariant provided you take two similar operators. So okay, so the way it goes is that if W is T-splitting, and if S is some linear isomorphism, then S is some isomorphism from V to V, then SW is STS inverse splitting. Okay, so and this is an if and only if. So this is a one-to-one correspondence between the splitting subspaces for T and the splitting subspaces for STS inverse. So it really depends only on the similarity class of T. Two similar operators will have the same number of splitting subspaces of any given dimension. Okay, so before we answer the question of existence of splitting subspaces, so let's recall some facts from algebra. So if you're given a linear operator on a vector space, and say you're given, okay, so given T, a linear operator T on V, then there is a natural FQX module structure on V, where we define the action of X by simply saying that X on V gives you TV. And then this V viewed as an FX module decomposes as a direct sum in the following way. So I can write it as a direct sum, I going from 1 to T, and then a direct sum J going from 1 to Li, FQX modulo the ideal generated by Gi to the lambda ij, where these Gi, G1 to Gt, are distinct monic irreducible polynomials, and these lambda i's, where each lambda I is defined as shown, that's an integer partition corresponding to this irreducible polynomial Gi. Okay, this is essentially the structure theorem for finitely generated torsion modules over a PID. Okay, so let's define LT to be the maximum length of, so we have these T partitions here, lambda 1, lambda 2 up to lambda T. So let's say that LT is the maximum of these LIs. So each LI is the number of parts in lambda I. Okay, so that's called the Frobenius index of T. So alternatively, this Frobenius index is simply, so if you look at the cyclic decomposition theorem, it's the number of summands there in that. Okay, and here is the theorem. So there exists a splitting subspace for T, that is sigma mn T is positive if and only if the Frobenius index of T is at most m. So this is a characterization of when there exists a splitting subspace for T. So it turns out that these T-splitting subspaces have practical applications. So before I come to that, so let me define what a Krylov subspace is. So suppose you have an n-dimensional vector space V over FQ, and you have a linear operator T on V. So suppose there is a subset S, which is V1 to Vm, that's a subset of V. Then the Krylov subspace generated by S under T is from a module point of view, it's simply the submodule generated by these elements, V1 to Vm. It's the FQX submodule of V that is generated by these elements. Basically, you look at sigma Fi to the T on Vi as Fi varies over polynomials over FQ. And let KMT denote the probability that if I choose an arbitrary tuple V1 to Vm, then the Krylov subspace generated by them under T is all of V. So basically I count the number of such tuples and divide out by the total number. So for each Vi, there are q to the capital N possibilities. And that's an M tuple. So that's the total number of M tuples I could consider, q to the N, whole to the N. That's the quantity appearing in the denominator. It was proved by Brent, Gao, and Lauder that if T has a Frobenius index L, and that you take an M that is at least equal to L, and you know the factorization for the minimal polynomial for T, then you can give a compact expression for this probability. Okay, in terms of the invariants that we defined earlier, those partitions and those irreducible polynomials. So here is a more general problem that they posed in their paper. So take a set S, V1 to Vm, and then define the truncated Krylov subspace. So how do we define that? So we again consider, so given these vectors V1 to Vm, we look at sigma I going from 1 to M, Fi to the T on Vi. But now, earlier we allowed these Fi's to be arbitrary, but now we restrict the degrees of these Fi to be at most N minus 1. Okay, and that is the truncated Krylov subspace. And analogous to the previous definition, we can ask, let KMNT denote the probability that if I take a random M tuple of vectors V1 to Vm, that the Krylov subspace spanned by these is all of V. Okay, so what can I say about this probability? So here is the problem. So I'm given these M and N and T. Can I compute this probability? The reason that this probability is interesting and relevant is that apparently even having bounds on this KMNT is useful because it gives bounds on the runtime of certain algorithms that are used to solve sparse linear systems over finite fields. Okay, so let's see. However, this KMNT is in fact closely related to this sigma MNT as we have defined it. So, in fact, it's not difficult to show that if you can compute sigma MNT, then this KMNT bears a simple relationship with this. So, if you compute sigma MNT, then you're all set as far as computing this probability goes. Okay, so let's look at some specific cases of where these splitting subspaces are known. So one can recast the result of Chen and Singh on splitting subspaces in the following way. So if you take a linear operator on a T on V, and it has irreducible characteristic polynomial. So again, we are assuming here that the dimension of V is Mn. Then sigma MNT is, well, simply given by this expression. And one can do the following. So suppose the invariant factors of T, so if this T is defined on an Mn dimensional vector space, suppose they have a particularly simple form. That is, let's say that the non-trivial ones are all given by the same polynomial. And let's say that there are precisely M invariant factors equal to G. Okay, so the number of those G's there would be M. And in this particular case, one can also compute the number of T-splitting subspaces of dimension M. This is joint work with Divya Agarwal. Okay, so as a corollary of this result, one can show that if alpha has a minimal polynomial, so an element in F2 to the Mn has a minimal polynomial of degree M, then I can still compute the number of alpha splitting subspaces. Okay, so I guess we are more or less out of time. So I had a few, maybe I'm going to give one more example. Maybe let me come to T-splitting subspaces. So here is another case where we can count the number of T-splitting subspaces. Suppose you are given a bunch of invariant factors for your linear transformation. So we saw that it depends only on the similarity class of T. So rather than looking at the number of splitting subspaces for T, we could just look at a bunch of invariant factors, and that defines a conjugacy class. So we could ask what is the number of splitting subspaces corresponding to that set of invariant factors. So it turns out that if you have these invariant factors, so there should be Mn invariant factors, but we saw that they are mostly going to be ones, except potentially for the last M invariant factors. And in that case, provided that the degree of the smallest invariant factor is n-1, one can show that the number of splitting subspaces corresponding to this conjugacy class is Ci by Ci tilde, where Ci for any tuple of invariant factors denotes the centralizer in the corresponding general linear group. Okay, so this defines a conjugacy class, and we can look at the corresponding centralizer size. So look at I. So I tilde is defined in a simple way in terms of I. And one looks at the centralizer of I in the general linear group of order Mn, and the centralizer of I tilde that comes from a different general linear group, one of order M. So the quotient of these two centralizers is the number of splitting subspaces. Okay, so maybe I'll say one last thing before we wind up. So recall that we had given a linear operator T on a vector space. You have this natural FQX module structure And there are these irreducible polynomials and these corresponding partitions. These GIs and the corresponding lambda i's uniquely determine this conjugacy class. And one can define, so rather than look at these tuples GI lambda I, which carry all the information about the conjugacy class, one can simply throw away the GIs and only look at their degrees. Okay, and that this multiset d1 lambda 1, d2 lambda 2 up to dk lambda k, that is called the similarity class type of T. This is a notion that goes back to Green in the context of his work of on the irreducible characters of the finite general linear groups. Okay, so the reason for this is that very often combinatorial properties don't really depend on the similarity class, but on this more general invariant, which is the similarity class type. So here we have thrown away some information. We are not really keeping track of the polynomials, but only of their degrees. And it can be shown that if you have T and T prime are two operators which have the same similarity class type, and let's say that they both are defined on some FQ dimensional, on some vector space of dimension Mn over FQ, then they have the same number of splitting subspaces. Okay, so one can go a bit further. So one way to prove this would be, an ingredient used in the proof here is a structured theorem on the invariant subspace lattice of a linear transformation. So given a linear transformation T, one can look at the lattice of all invariant subspaces. Okay, that's a partially ordered set, and one can define a meet and join, which makes this into a lattice. When the similarity class type of T and T prime are the same, it turns out that one can not only give a lattice isomorphism, one can give a dimension preserving lattice isomorphism. And one can use that fact to say that the number of splitting subspaces is the same. And even more, so suppose you are only given a similarity class type tau. Then this quantity sigma md tau, one can show that it's always a polynomial in Q. Okay, so this again is joint work with my student Divya Agarwal. Okay, so if m and n are fixed, then this sigma md tau is always a polynomial in Q. So the number of splitting subspaces is always given by a polynomial. I think that I'll stop here.
Yeah, thank you. Thank you, Sunday. It's very nice book. It's really nice to see how the have blossomed and you're family responsible for this. So it's open for questions.
Yeah, sure.
Anybody has any questions, comments? Some compliments in the chat box. Yeah. Abhishek has a question. Is there a formula to find the number of Mn block companion matrices for a given polynomial that is not necessarily irreducible over Q?
Okay, so that's quite an interesting question. I believe that there is no general answer known to that particular question. To find the number of block companion matrices, so for by a given polynomial, I'll assume that you mean the characteristic polynomial, right? So as far as I know, that there is no answer known to that problem. I believe that that's an open problem.
Mm-hmm. More questions? So I just wanted to ask, so do you think you have hope of getting a good answer for the splitting subspace problem
For
in
which
general?
this sigma MDT? I believe that the answer is no. I believe that for a general T, this may be a very complicated problem.
Yeah.
There have been some other cases where, so in fact, in all the product formulas given so far, it turned out that this sigma MDT, at least in all the problems that I spoke about in this lecture, it turns out that this sigma MDT is always a power of q times some product of, powers of q minus 1. In other words, maybe a product of some cyclotomic polynomials in q. But it turns out that there are some cases where they may not even be cyclotomic polynomials. So the roots of that polynomial did not necessarily all lie on the unit circle. So, and also one may not be able to expect a simple product formula. That's what it seems like. So I believe that it may not be so simple for general T to give a nice answer.
Okay.
That's my gut feeling, but I could be mistaken.
And what's the technique you use to show that this quantity is a polynomial in Q?
Oh, that's yeah. So in fact, to show that this is a polynomial in Q, one way to show this would be to use. So there is this pioneering paper by Delsart, published in the Annals of Math, where he computes the number of. So if you're given a P group of type lambda, one can ask how many subgroups of type mu are there. So lambda is some partition and mu is some partition. And he showed that there is a nice product formula that one can give in this case. So one can actually use that result to say that this is a polynomial in Q. One way to prove it would be to use it.
So that should be related to Hall polynomials.
Yes, indeed. It's related to Hall polynomials and the Hall algebra and so on. That's right. That's right.
Okay, very nice. And I hope you will share the slides with us.
Sure, I'd be happy to share the slides.
Please do that.
Thank you, Samrit. This is Arun.
Okay, so we have a break about, thank you so much, Samrit, for your 2 lectures. Very nice talks. Thank you.
Thanks.
I don't know if you lab virtually or whatever. All right, so let's have a break of about 23 minutes or so, and then come back with our second last talk of the workshop.
Hello. Shall I share my screen?
Yes, Mrinmay.
Okay, fine. I'll do that.
Hi, how are you?
Yeah, I'm good. How are you?
I'm good. Sorry, I couldn't attend your lectures before. Two lectures before.
Okay, no problem. You wrote to me separately. Yeah, so I also missed quite a lot of lectures.
yeah. Actually, थोड़ा सा weakness है उसलिए.
Okay.
Okay, you can start.
Yeah. Okay. So you can hear me, right?
We can hear you.
I do not know. I cannot hear you.
Yeah. Mrinmay, we can hear you.
Let's see.
Hello, Mrinmay. Am I audible to you? Mrinmay.
Can you hear me?
Yeah, Mrinmay, can you hear me? Mrinmay.
There's a problem of one.
Yeah, I can hear you.
Perhaps Mrinmay do not hear us.
I cannot hear you, but anyway, so let me begin. And if you have questions, please write on the chat box. So here is where we are. So we were talking about we were talking about the problem of determination of generalized Hamming-weights of Reed-Muller codes, and we have also shown that we started with this problem of error correcting codes, which is actually the determination of the Reed-Muller codes. We have translated this to a problem of algebraic geometry, which was rather elementary in nature. And then what we did was that we went from this algebraic geometric problem to a problem of extremal combinatorics. And if you recall the notations that we have been using, so this is the quantity that we are trying to determine, ERADN, which is the maximum possible number of common zeros of a system of R linearly independent polynomials, reduced polynomials, each of degree less than or equal to D. Okay, and we have shown that ERADM is less than or equal to maximum possible number of footprints given by R elements in a hypercube, so to speak. So just to make sure that you recall what we were doing, so here we drew pictures like this. So we said that the shaded areas is called a shadow of these 4 points, and our problem is to obtain an optimal configuration which will help us optimal configuration which will give us the least amount of the shadow. So here, as I have said, we have 4 points, and the case that we are dealing with is the case when m is equal to 2. Okay, so what we can do, I will first give you an idea of where we are going. So it turns out that in the case when m is equal to 2, and here I have taken so q equal to 17 and d equal to 12, and in what way we could put these 4 points either on this green line or below the green line, so that the so that the cardinality of the shaded area or the area of the shaded area, however you want to see it, is the smallest. And it turns out that we have to somehow tuck all these points systematically in one of the corners. So for example, this corner, or since there are a lot of symmetries in this picture, we can also do it here. And what do I mean when I say that I have to tuck all these points in a systematic way in one of the corners? So this is where the language of lexicographic orders and all these things come in. So I will go through the results that are known regarding these things in some detail. So, let us see. So actually here I had to make a call between whether I will give you a complete proof of this result, or I will tell you kind of a literature survey on this. And what I thought was that if I wanted to prove this result explicitly, it will be first of all very technical, and it will be very difficult to finish within 1 hour. So I have taken this freedom to choose the next option. So here is the question. So F is a hypercube with the length of the side q, if you want to look at it this way, or each side having q distinct points. So it is the m times Cartesian product of the set 0, 1 to q minus 1. And we have to determine a subset consisting of r distinct points of fd. So this is not f less than or equal to d. Here we are asking in what way we could put these points on this green line, not necessarily below. I mean, not below at all. So on this green line, such that their shadow is going to be minimum. So this is the question that has been historically considered in extremal combinatorics. I will show you who have worked on this and what are the results. So I hope that the question is clear. So here are some results. So for q equal to 2, if all the sides have length 2 of this hypercube, then the answer is known to be a famous theorem in combinatorics, which is known as Kruskal-Katona theorem. So Kruskal and Katona were two different mathematicians, of course, and they have written two independent papers on the same topic, and the references are given here. If you are interested, you could look at their original papers, or you could also look at this book by Bela Bolomos, which is titled as Combinatorics. So here these results appear. And so what is the result? So they say that this minimum, so this optimal configuration is given by taking the first R points on FD in descending lexicographic order. So this is one way of saying this thing. So what I mean by descending lexicographic order, it means that I have to choose my points starting from here, and I have to put first 4 points on this line over here. So again, as I have said that this figure particularly have a lot of symmetries, and you could also choose these 4 points. So then you can actually prove that the shadow of these 4 points is actually equal to the shadow of these 4 points. But then it is called, how would you represent it? It is called reverse lexicographic order probably, but let us not talk about all those things. So this is one optimal configuration, and we are going to stick with this. So we have to choose R points in this way. That is the R points, R largest points in descending lexicographic order, and that will give me an optimal configuration. So what happens if I ignore this condition when q is equal to 2? Can we do it for arbitrary values of q? The answer is a consequence of one theorem by Macaulay, which goes back to 1926, far back, far before when Kruskal and Katona's papers were written. These are only in 1963 and 1968. But to be honest, this result is only a consequence of what Macaulay's result does. So in particular, what he considers is an infinite hypercube. So if not even, I mean, the sides of the hypercubes are not even bounded, not even finite. Okay, but one can derive this result from the Mac-Calais theorem. And what is the result that we are looking at? The result is exactly the same. The optimal configuration again is obtained by taking the first R elements or for first R points on FD in decreasing lexicographic order. So I'm sure that the slides will be put up somewhere, and if you are interested, I have also given the references to these papers in this corresponding slides. So as I have mentioned, this is the picture. So you could take Q to be anything, and in order to obtain the minimal or the optimal configuration, you have to put your points like this. So this is the result. So now one could actually ask a more general question. So what happens if we consider a hyper rectangle, which is not necessarily a hypercube? So what do I mean by that? So hypercubes have sides of equal length, but hyper rectangles, they do not need to have that condition. So this is just an higher dimensional analog for rectangles. So namely what we are doing, I take a sequence of integers, increasing sequence of integers, d1, d2, dn, and I take f to be the Cartesian product of this set. So first, the set consists of d1 many points, second set consists of d2 many points, and the last mth set consists of dm many points. So then for an integer d bigger than or equal to 0, I consider fd to be the set of all m tuples from this set f, such that their degree is equal to d, that is their sum of all the coordinates is equal to d. So then we can again ask the question, what happens or how can we choose an optimal constellation or configuration of R points such that the shadow of these R points is the smallest? Okay, so this question was answered by Clements and Lindstrom. So this is after the Cartona's paper, Kruskal's paper also. So again, you can see that the similar kind of results are obtained here. So the minimal configuration is obtained when you take the points to be the first R points on FD in decreasing lexicographic order. But here one needs to be somewhat careful. So for example, here the picture will look like this. So suppose that this is the side with d1 many points and this is the side with d2 many points, and suppose that this is our line x plus y equal to d. But then what Kruskal and Katona say that you can again choose the points in this way. But on the contrary to the other problem where I have considered the special case of hypercubes, I cannot here take the points from here because the symmetries that we have in the cases of hypercubes are completely lost because we have the condition, I mean, in the case when d1 is less than d2. So this is a short review of the problem when we are considering this the points to be lying on FD, that is on this line. And so now we are ready to look at the question that we are interested in. So again, I take F to be the hypercube with length of each side equal to Q. And I ask, how do I construct a set of R points in F less than or equal to D? So this is the problem that we are actually interested in, such that the shadow has the minimum number of points. Okay, so the first result to this end, as far as I am aware of, is by Victor Way. I have given you the reference. So where he actually introduced the notion of generalized Hamming weights. So he was interested in computing the generalized Hamming weights of binary Ritmuller codes, and he did not actually follow the idea of monomial ideals and other things that we have developed, but he has somehow reached this place in a different way. And he again had to answer this question: how can we prove these R points so that the shadow is the smallest. And for this case also, he proved that this minimal shadow is obtained when A1, A2, AR are taken to be the first R consecutive points from S if less than equal to D in descending lexicographic order. When Q equal to 2, the case if D was solved by Kruskal-Katona's theorem, so it was quite evident that Way made use of this Kruskal-Katona theorem in a strong way to arrive at his theorem. But do remember that what he has done is for the case when Q equal to 2. So the next thing in line has to be for arbitrary values of Q. And now you probably get an idea that if you want to generalize this result of B, where he has considered binary Dickmuller codes, or the case when Q is equal to 2, where he used Kruskal-Katona theorem, one of the ingredients for this arbitrary value of Q has to be either Clemens-Lindstrom theorem or Macaulay theorem. So this is what Heinen and Pelikan have done. So they were interested in computing the generalized Hamming weights of the Reed-Muller codes that we are talking about today in this lecture, and what they have shown is a result of same kind, that you have to choose your points, your R points from the set F less than or equal to D in descending lexicographic order in order to achieve this the smallest shadow. Okay. So here there are a few remarks that I want to make. So if you look at this paper, Heinen-Pelikan, the result or this result in a different form occurs in probably in a theorem called theorem 5.7. And what they did is the following. So they said that, okay, so we have Kruskal-Katona theorem, which we have used to give this result that I have just mentioned. And now we have a generalization of Kruskal-Katona theorem, which appears as either a consequence of Macaulay theorem, or you can also call it Clemens-Lindstrom theorem, I mean the consequence of Clemens-Lindstrom theorem. And then we can actually use the same way that Way used to prove his result. And that is their proof. They did not give an explicit proof of this fact. And as I have said, they have only mentioned that the proof of Way using Kruskal-Katona generalizes to the proof of this theorem 5.7 by using Clemens and Lindstrom theorem. Okay, but then there was a problem that we came across when we were reading Way's proof of this theorem. We found a mistake, and then the result that Heinen-Pelikan have proved, and even the result that Way have proved, were correct, but as I have said, that Way's paper contained a mistake in their proof. So in principle, it is our shortcoming that we did not get a complete proof of this fact. So who are we? So this was part of a joint work with Professor Peter Whalen. So then we were also trying to generalize this to the case of a much more general class of codes, which are known as affine Cartesian codes. So here we have our theorem. So first, the question is that if we take a hyperrectangle, which I have just mentioned, and then again, if I consider F less than or equal to D, how can we choose our points in F less than or equal to D such that the shadow has the smallest number of elements? And here is our answer. So this is available in the paper that I have mentioned here. So you will find a full proof of this result. Okay, so again, our result has to be the same, and our result says that the minimal, the optimal configuration is obtained by choosing the R points on F less than or equal to D in descending lexicographic order. So here is the picture. So here again, n is equal to 2, and I do not know when I drew this picture what is the value of d1 and what is the value of d2, but it is clear from the picture that d1 is less than d2, or d1 is less than or equal to d2. So I have considered this rectangle, and this is our line x plus y less than or equal to d. So we are considering this region, and we are asking in what way we can prove we can put our points in this region, either on the green line or the shaded region, so that the shadow of the set of our points is going to be the smallest. Okay, so here is exactly how we do it. The first point is this one. This is the topmost point in the descending lexicographic order in this set, f less than or equal to d. And then I chose this point, this one, and so on. So this is how we have to arrange our points. So in particular, you can see that when we put d1, in particular, when we put d1 equal to d2, which is allowed, of course, in this case of this hyperrectangle, because we have allowed this this non-strict inequality, so to speak, over here. So if I took d1 equal to d2 equal to dm all equal to q, then we actually get Heinen-Pelikan's result as a consequence. So as I have said, I have given you the reference. If you want, please go and have a look at the proof. Okay, so now what I have said up till now is that in what way I can get this optimal configuration. But then the question arises, so okay, I have now given you an optimal configuration, but then given an optimal configuration, can I actually compute the cardinality of the shadow? So this is what our goal should be, because we are not only interested in computing, in asking for what are the leading monomials of the polynomials that we are considering, so that they will give me the higher weight, rth higher weight. So we also want to compute what are the higher weights of the generalized Riemann codes. So that means we have to somehow determine the optimal cardinality of these shadows. So I have skipped the proofs before, but here I want to do some computations and show you how things are done. So I will stick to the case of Heinen-Pelikan, because I am only talking about generalized Riemann codes and not exactly affine Cartesian codes. So why bother? So I take f to be equal to the hypercube, which is given by the m-fold Cartesian product of the set 0, 1 up to q minus 1. So here is our first lemma. So let me call it lemma 1 for our convenience. So suppose I take r to be any point, any non-zero integer between 0 and q to the power m minus 1. So actually I am taking the set 0 to q to the power m minus 1 with q to the power m minus 1, which has q to the power m points. And also you can see that this f has also q to the power m points. So there is a bijection that we are going to consider, which will help us in proving the lemma. Before that, what is the lemma? So suppose I take r to be a point on this set, and I can write q to the power m minus r as summation ai q to the power m minus I, where I varies from I to m. So you can view this as a QRE representation of this number. So this AIs are going to be unique. So then the claim is the tuple that you can form, the m tuple that you can form by taking this A1, A2, AM, this is the rth tuple of F in descending lexicographic order. So this is the rth tuple of the hypercube in descending lexicographic order. And also the converse is true. What should be the converse? So you take the rth tuple, which is given by A1, A2, AM, then q to the power m minus r can be written exactly as this sum. So the proof is not very tough. What I do is that I construct a bijection between F and the set that I have just mentioned, the non-negative integers between 0 and q to the power m minus 1. So how do I construct this? I take a m tuple and I send it to a sum. So this is summation I from 1 to m ai q to the power n minus I. Now, it is clear that phi is surjective because, as I have said, that every integer must have a q-ary representation, which is given by exactly this polynomial. I mean, okay, so this expression of the polynomial, and now these two sets have same cardinality. If a map is surjective, it has to be a bijection. Moreover, if I take 2 points, a1, a2, am, and b1, b2, bm from the set F, I can see that here this lexicographic ordering occurs, that is, the point A is in lexicographic order less than or equal to B, if and only if this inequality is true. So this is actually not very tough to show, but if you want to work out, I will leave this as an exercise. Okay, so then what we are getting is that I have this set F and I have this set of non-negative integers from 0 to q to the power n minus 1, and I have got a bijection which is sort of order preserving. So here I have a natural order which is lexicographic order, and here I have a natural order which is just less than. So this is an order preserving bijection in this way. So the rth elements in decreasing order from this set, rth highest element of this set will correspond to the rth highest element of this set. So what is the rth largest element of this set? This is exactly given by q to the power n minus r. And what is the rth largest element of F? So this is what is going to be a1, a2, am, for example, what is given. And so we are going to get this equality. So since we have a bijection, the converse is also true. Okay, so I think I still have quite a lot. So this is our lemma 2. So suppose I have R elements, the first R elements in descending lexicographic order from F less than or equal to D, and then what are the elements of the shadow of this A1, A2, AR? And it turns out that the shadow is given by exactly the set of all elements in F that are lexicographically larger than or equal to AR. So if you remember the picture that we have drawn here, you can easily see. So what is the shadow? The shadow will be so this shaded region, and you can pick up any point from here. You can see that this will be larger in lexicographic order from one of these elements. Okay, so this is what we are going to prove now, and this claim will imply something about the cardinality of this shadow. So let us first prove this first claim, and I will come to the second claim once I have done this. So this is somewhat technical if you are seeing this kind of things for the first time. So suppose, so what I have to do, naturally I have to prove an inclusion in this way and another inclusion in this way. So why don't I take a point in the shadow first, and I try to prove that this point will be bigger than or equal to some AIs or AR in particular in lexicographic order. Okay, so A belongs to the shadow, so that means what? That means it has to be bigger than or equal to some AI in the partial order. Now, if this element is bigger than equal to this element in partial order, then it must be true that this element is bigger than or equal to AI in lexicographic order as well. So this is what we have used. And since A1, A2, AR are the largest elements in decreasing lexicographic order, AI has to be bigger than or equal to AR in lexicographic order. And so what we have shown that this A is bigger in lexicographic order than AR. So we have proved this inclusion. So now we are trying to prove the other way inclusion. Okay, so what I will do now is that I will take 1 point from F, which is larger than AR in lexicographic order, and I will show that it belongs to the shadow. Okay, so let me call this point to be equal to B. And so B is bigger than or equal to AR in lexicographic order. So there are two cases. So it could be so that B is equal to AR. So if B is equal to AR, then B lies in the shadow of AR, and which is a subset of the shadow of all other points. So this case is trivial. So then otherwise what can happen is that B is strictly bigger than AR in lexicographic order. Okay, so now I write B as B1, B2, Bn, and AR as AR1, AR2, ARm. Okay, so now I know that B is bigger than, or B is strictly bigger than AR in lexicographic order. By definition, there must exist a T less than or equal to M, such that as long as I is less than T, Bi has to be equal to ARI, and the T plus 1th element, T plus 1th component of B, which is Bt. So that has to be, so it is less than T, and this is the Tth component. This has to be bigger than the Tth component of this element. Okay, so now this is a strict inequality. What we obtain here is that Bt is bigger than or equal to ART plus 1. So now I will construct a C. So what is C? C is C1, C2, Cn, where Ci is equal to ARI when I is less than T, ART plus 1 when I is equal to T, and 0 for all I which is bigger than T. Now it is clear, which I will illustrate also. Why is it clear? But you can see from this, from the way we have defined it, that it is clear that B is bigger than or equal to C in partial order, and also C is bigger than or equal to A in lexicographic order. So let us also try to see that. So what are these elements A, R, B, and C? So AR, so suppose I can write it in this way: AR1, ART minus 1, ART, and ARM here. B. So for first T minus 1 elements, components, they will be equal. So I can put AR1, AR2, ART minus 1 here. Then I have a BRT, which I have derived that this is bigger than or equal to ART plus 1. And then I have something that I do not have any control on. And what is C? So again, for the first few elements, in fact, T minus 1 elements, they all are equal. Here I have put ART plus 1, and then rest all the elements are equal to 0. So then you can see that since all these elements are bigger than or equal to 0, and of course here this element is bigger than or equal to ART plus 1, B is bigger than or equal to C in partial order, and also it is clear from this coordinate representation that AR is less than C in lexicographic order. Why is that? Because the first T minus 1 coordinates are equal, and the first place where they are not equal, C dominates AR in that coordinate. Okay, now we claim, or it is also easy to see, that the degree of C is bounded above by degree of AR plus 1. So you can just realize it by looking at this coordinate representations. So now there are two possible way out from here. Either degree of C is equal to degree of AR plus 1, or degree of C is strictly less than degree of AR plus 1. So let's see what happens in this case. Degree of C is equal to degree of AR plus 1. So here, so when is it possible that the degree or the sum of all these terms is same as the sum of all these terms minus 1? So sum of all these terms plus 1 is same as the sum of all these terms. So then all these things here for A has to be equal to 0, AR. So this is what we are getting. So AR has to be equal to AR1, AR2, ART, and then all 0. And we can see that C in partial order is bigger than or equal to AR. Okay, so in this case, we already had B is bigger than or equal to C in partial order. And now I have proved that C is also bigger than or equal to AR in partial order. So B is bigger than or equal to AR in partial order, and this is something that we wanted to prove. So next, the case is degree of C is less than, it is strictly less than degree of AR plus 1. And what is degree of AR? It is bounded above by D. And so we have that this is less than or equal to D plus 1. So we have a strict inequality here. So noting that, I can write that degree of C is less than or equal to D. And as I have claimed that C is bigger in lexicographic order than AR, then what are the possibilities? So C lies in F less than or equal to D, and C is bigger in lexicographic order than AR. Then C must be one of the AIs, because remember that what were A1, A2, AR? They were chosen to be the first R elements of F less than or equal to D in descending lexicographic order. So, well, C has to be equal to AI for some I equal to 1 to R. And if they are equal, so then C is bigger than or equal to AI in partial order. And it follows because again, I can refer to this inequality, and I can apply the same argument, and this will show that B is bigger than or equal to AI in partial order. So in either cases, what we have shown is that B belongs to the shadow of A1 into AR. So we have proved the first part of our theorem. So this was the first part. So now I have a systematic way of representing all the elements of our shadow that we are looking at. And then can we compute the shadow? So here we want to compute the cardinality of the shadow. So this has to be the cardinality of this set. And you can see that the cardinality of this set is actually determined by this AR. So let us see how do we determine it. So as I have said, the cardinality of this shadow is determined by AR. So in particular, we are looking at all possible elements of F which are in lexicographic order bigger than or equal to AR. So let me call this number S. So what is S? So S is the number such that AR is the Sth element in F in decreasing lexicographic order. And now lemma 1 applies, and it tells me that this number S is exactly equal to Q to the power M minus summation of this quantity. So recall what are these ARIs? So AR was represented in this way, AR1, AR2, ARN. Okay, so now I can compute my optimal shadow as well. And in fact, you will see that this is going to be the formula for the generalized Hamming weights. But wait, there are something to say. So if the shadow is equal to this, if the optimal shadow is equal to this quantity, what is the cardinality of the footprint that we were looking at? So this will be just Q to the power M minus this whole quantity. So this is going to be summation ARI Q to the power N minus I. And what are these quantities ARI? This is the coordinates of the Rth element in descending lexicographic order chosen from F less than or equal to D. So this is getting complicated at this stage, but if you go through the proof, it will not look that complicated. Okay, so now we have this. So we have shown using the deduction that we have made on the previous day that ERADM is less than or equal to AI summation AI Q to the power N minus I, where A1, A2, AM is the Rth element of F less than or equal to D in descending lexicographic order. So when I am stating a theorem in this way, I do not need to make the notations complicated by putting AR1, AR2, ARN, but we know now how we have derived it. So the proof is easy. It follows from how we have actually come from the coding theoretic problem to the problem of combinatorics. But now the question is it a strict inequality, or can equality also occur? And is there any reason a priori to believe that this inequality is not going to be strict? Probably not, because if you remember how we have come from the notion of this APR, ADM to the notion of the shadows, we have ignored so many things. So first of all, we have said that, okay, if I take a system of polynomials, then okay, so I said that AHF J of U is less than or equal to AHF of the leading term ideal of I of U. And what was the leading term ideal of I? Leading term ideal of I. Okay, so what was I actually? I was generated by all the polynomials of this form, xi to the power q minus xi, and then the leading terms of f1, leading terms of f2, leading term of fr. So we were considering this ideal, and we said that this okay, so here there was a reverse inequality, HF mu J, and we said that the monomial ideal, which is generated by just taking the leading monomials of the generators, so that is, so here we have F1, F2, F1, F1, F2, F1, sorry. So we said that, okay, so the leading term ideal of I contains the ideal generated by x1 to the power q, x2 to the power q, etc., and the leading terms of fi. I varies from 1 to r. So here we have ignored a lot of things. I had mentioned when I was talking about the monomial ideals or the leading monomial ideals that this ideal may not be equal to the leading monomial ideal, leading term ideal of this ideal that we started with. So there is a priori no reason to believe that this inequality will ever be an equality after all. But here magic happens as I view it, because I really have no explanations for this. The magic is that I can actually, or one can actually produce a system of R polynomial equations where the polynomials are linearly independent such that they have exactly this many zeros. And this is something that I want to finish this lecture with. So given an element B in F, I define a polynomial F suffix B in this way. So I take this double product where S varies from 1 to M and T varies from 1 to ds. So well, what is ds? So this is one of these coordinates that is given here, and I write it as xs minus gamma t. So t will come from 1 to the SF coordinate here. And what are this gamma t? So here I have fixed an enumeration, or I have fixed an order of all the points in FQ. So FQ has Q points, I write them as gamma 1, gamma 2, gamma Q. So if P was a prime number, if Q was a prime number, there was an obvious choice. I could have written the elements to be equal to 0, 1 to Q minus 1, but since Q is a prime power a priori, this is not possible. And so I have to take this way to come to our conclusion. So what is degree of FP? So what is degree of FP? So if you want to count, you can see that that xs, so this will be, so what will be the leading monomial? So this will be x1 to the power something, x2 to the power something, xn to the power something. So what is the coefficient of, I mean, what is the index of x1, for example? You can see that this is clearly equal to b1. So x2, this is also going to be equal to b2, etc. And this is bm. So the degree of FP is going to be the same as degree of B. Okay, so given a point, I come up with a polynomial with the same degree as the point, and also if B is an element of F less than or equal to D, then degree of FP must be also less than or equal to D. So okay, so given a point, I come up with a polynomial with the same degree as the point. Now there is a bijection from FQ to the power M to F that we can define, which is defined rather trivially. So gamma T1, gamma T2, gamma Tm, note that these are all elements of FQ. So I send it to T1 minus 1, T2 minus 1, Tm minus 1. You can see that this is a bijection. And moreover, what is important is that you will see that this f of b is non-zero at a point of fq to the power m if and only if the image of this point in f lies in the footprint of b. So this is excellent. So this is how this works out. So what happens when fp is equal to 0? So fp is equal to 0 at a point if and only if the image of this point under this map psi lies in the shadow of this point. So we can now take union and do all kind of things. So now for A1, A2, AR in F and the point gamma, we can see that this gamma belongs to, the point gamma is a common zero of these R polynomials if and only psi of gamma falls in the shadow of this R points in F. And as a consequence, the number of common zeros of this polynomials will be exactly equal to the size of the shadow of this polynomials. And this is not only true for the points which are chosen in a way that we want to choose. This is true for every point which lies in F. So now if we take A1, A2, AR to be the first R elements of F less than or equal to D in descending lexicographic order, and if I denote AR by this quantities AR1, AR2, ARM, then we already know what is the number of points. This is the number of points that we have determined before. And once we know this number of points, we know, so this was an upper bound. So we had shown that this is bigger than or equal to ER ADM. But then we have produced a set of polynomials for which the number of zeros, common zeros, attain this bound. So what we have is that this must be an equality after all. So ER ADM is given by this quantity. So then what is left? So now it is going to be trivial. So what is the Rth generalized Hamming weight of the Reed-Muller code that we have defined during the last lecture? So this is simply going to be q to the power m minus ER-ADM and ER-ADM. This is something that we have already determined. So this is actually the result that Heinen and Pelikan proved. Probably in a different flavor that you can see. You will not see that this point is the Rth point on F less than or equal to T in descending lexicographic order, but he has they have a different way of representing this, but this is essentially what is going on. Okay, so now when Professor Sudhir Khorpade was lecturing, he talked about the minimum distance of Reed-Muller codes. And for a general case, as far as I remember, he did not give a proof of the same. And he gave a proof in the case when D is less than Q. Okay, so if D is less than Q, he showed that the number of zeros of a polynomial is bounded above by this quantity D times Q to the power m minus 1. And of course, this bound is attained by one of the polynomials. And consequently, the minimum distance of this Reed-Muller codes is given by Q to the power m minus D times Q to the power m minus 1. So the formula is Q to the power m minus 1 times Q minus D. Okay, so just a passing remark, when I was attending the first lecture by Professor Alberto, he finished his first lecture with a fact that if you have a polynomial of degree D or degree less than or equal to D, f of x1, x2, xm, so the degree of f is less than or equal to D, which is less than Q, then this polynomial must have a non-zero in fq to the power n. So this also follows from this fact easily, because if D is less than Q, then this guy is always positive, and consequently the number of non-zeros of a polynomial is always going to be positive. So this is a proof, for example. So now what I am going to do is that I am going to give formula, a general formula, and along with a proof using the formula that we have derived here when we were interested in computing the generalized Hamming weights. Note that I have said in the previous lecture that when I put r equal to 1, what I get is the minimum distance. So let me compute the minimum distance of the regular codes. Okay, so here is the formula that I get immediately from here, from this corollary. So what is the formula? This minimum distance is going to be given by q to the power m minus summation I equal to 1 to m ai q to the power m minus I. And what are these AIs? AIs come from the coordinates of the rth element of f less than or equal to d in descending lexicographic order. So now, so this is a good enough way to say that this is the minimum distance. But let me try to simplify this a little bit. So now I take d, which is given here. So I can always write d to be equal to theta times q minus 1 plus l, where l is strictly less than q minus 1. And then we are considering the set f less than or equal to d. Now, if you look at it carefully, you will see that what is the largest element of this set f less than or equal to d in decreasing lexicographic order. It will be given by exactly this quantity. So q minus 1, q minus 1, q minus 1 theta times, and then l, and then all zeros. So this is the largest element. And then this will serve as our a1, a2, a theta, etc., a theta plus 1, etc., am in the formula that is given here. So now it is only a matter of doing this, putting this information in the formula that we have derived as a corollary of the generalized Hamming weights. Okay, so now this is really a very easy calculation which I have done carefully, and the final formula comes to be equal to this. So minimum distance is given by q to the power m minus theta minus 1 times q minus l. A reality check would be to go back to something that Professor Ghorpade had already shown you. So if d is less than q, so well, so for example, let me take d to be less than q minus 1. So this is also a special case of his case as well. So then theta is equal to 0 and l is l. And what do we get from this formula? We are going to get and L is equal to D. So this is my point. Okay, so if I put theta and L in this formula, what I am going to get is q to the power m minus 1 times q minus D. So this is exactly the formula that we had here for the minimum distance. This is all I had to say, but I was talking to one of the participants and she asked me to say about some possible open problems in this area. So I did not make slides on this, but since I have time, I could informally tell you some things. So one of the questions is that the proof that I have given you is not geometric. So we do not know the geometry of the hypersurfaces, which gives us this bound. So this is of course a classification problem, which is interesting from a geometric point of view as well as coding theoretic point of view. That what is the configuration of R such polynomials or R such hypersurfaces which give me this bound that we have determined. As far as I know, this question is not solved, partly because when we are following this kind of an approach that we are following here, the geometric interpretations or the geometric intuitions are quite hidden, and it is not clearly visible what is going on geometrically. So there are other problems which are related to determination of weight distributions of Reed-Muller codes, and well, I don't think that after the second weight anything is determined in literature, so this is an open problem. So there are some further generalizations of the combinatorial problems. and also the problem of determination of generalized Hamming weights that I have mentioned now. So what are the problems? So this is something related to determining the relative generalized Hamming weights. So relative generalized Hamming weights of Reed-Muller codes, or even affine Cartesian codes, which I have not really talked about, but I have told you the problem, the combinatorial problem, which is related to affine Cartesian codes. And this is actually very interesting when you look at the problem combinatorially. So here, what is the problem? So here we are going to consider a rectangle, and we are, instead of having one line, I'm going to take two lines. So suppose that this is one of the lines, and this is another line. So what are the equations of these lines? Suppose that this line is given by the equation x plus y equal to d1, and this line is given by x plus y equal to d2. And one asks, in what way I can put my R points in between this shaded area so that the shadow is minimum. The same problem, but here we have an extra condition that the points have to lie either on this red line or above. So this actually contributes to the determination of relative generalized Hamming weights of Reed-Muller codes and affine Cartesian codes. This problem was solved by Olaf Kiel and his collaborators. Let me write it all. I do not remember the name of the other collaborator. And I could solve this problem, and this has now appeared in the journal called Designs, Codes, and Cryptography. So this is all that I probably wanted to say, and thank you for your kind attention.
Thank you, Mrunmay, for a very nice talk.
Thank you.
So now you can hear me.
Yeah, I have now moved myself to the laptop.
Okay, very good. Yeah, no, it's really a beautiful result, and I'm glad you gave an exposition of it because people get an idea.
Yeah.
I mean, anyone of us who has seen the paper of Heinen and Pelikan would know how it's not so easy to read and understand what's going on.
Right.
I guess you mentioned open problem about weight distribution. I mean, finding the number of, let's say, subcodes of a given weight, or as you put it, finding the combination of hypersurfaces at the boundary. Of course, I just wanted to remark that for R equal to 1, this is known. I mean, the codewords of minimum distance, and that's the classical work of Delsart, Bothels-McWilliams, for example. But I do not know if for R greater than 1, this is known in any case.
Right.
Masood, you have a question or a comment?
I would like to ask if minimum distance or higher weights are known for toric codes. Do you know that? Because there is a relation between affine Cartesian codes and toric codes. I think they are more general. Is that true?
So there are results. Yeah. I mean, I know what you are saying probably. So what they do is that they take the projective spaces, so an n-dimensional projective space, and they only consider points which have all the coordinates that are non-zero. And then they evaluate some polynomials, homogeneous polynomials of degree d, etc. So that is exactly a consequence of a more general result that I have presented, or I have not presented, but I have just alluded to. This is a joint work with Peter Millen. So we have determined the affine Cartesian codes, I mean the generalized Hamming weights of the affine Cartesian codes, and one could easily derive the generalized Hamming weights of the codes that you are mentioning. but I am not sure whether those codes are called toric codes. So what I know that they are called codes from projective torus, which is probably a sensible term to talk about. But toric codes, I think they are somewhat different than this. But I am not a specialist in it. I have never worked with this.
Okay, thank you very much.
Yeah, most welcome.
I couldn't hear everything you said because of connection problems. Did you say that? Did you say that affine Cartesian codes are general than the torus inside the projective space?
Yes, yes. You could take one of the coordinates to be 1, and then what you get is an affine Cartesian code with all the sides of the rectangles equal.
Okay, that's true. Okay, thank you very much for the beautiful talks, both talks, and for this answer.
Thank you.
Any other questions or comments?
Hi, I have a question. Hi, Brunmai.
Hi. How are you?
Yeah, I'm fine. Nice talk, actually.
Thank you.
A lot. And I have a couple of questions which, they are questions because I have not seen such things before, but probably they are elementary, but I'll nevertheless ask. So the relative generalized Hamming weights that you sort of described, is there some sort of quotienting process involved? Do they arise as generalized Hamming weights of some other codes?
I mean, relative generalized Hamming weights are generalizations of the generalized Hamming weights. So, for example, if you take the red line to be below the wedges, then you are going to get the generalized Hamming weights. So, this guy is what you are considering. I mean, what one considers as the set of R polynomials that are linearly independent, whose degrees are bounded above by D1 and bounded below by D2.
Right. But this smaller code that you take, I mean, one can think of it as a subspace and quotient it. So, I mean, I'm not sure, but does it really correspond?
Maybe you tell him in the language of C1 and C2, the general definition.
Yes. So what do one mean by quotienting? I am not sure. I mean, there is this. So as linear subspaces, it might be same as quotienting, but when you have this Hamming metric, then what is the effect of quotienting? Well, I have never thought about it.
Right. Okay. So one doesn't know how the metric will respond.
Yeah.
Okay. And another question of a similar nature. Once you know these parameters, generalized Hamming weights and relative generalized Hamming weights, is it immediate for the tensors for multiple copies of similar codes? If you take tensors of Reed-Mullers or something like that with different parameters?
I don't know. Sorry.
Okay. Okay, thanks. But anyways, nice talk. Thanks.
Thank you.
Yeah.
Any more questions or comments?
So I wanted to introduce Lakshmi to you. So he is a faculty in electrical engineering department in IIT Hyderabad.
Oh, hi Lakshmi.
He works in things like network codes and other things.
Hello, Professor. Nice to meet you.
Yeah, nice to meet you. Yeah, I think you asked questions earlier this morning, right? I mean, this afternoon rather.
Yeah. So I think it was during August talk. Yeah.
August talk. Yeah.
And
thank you for participating.
Organizing this workshop. I think I had a very good time. Thank you so much.
I'm glad to hear that. Yeah, I guess we will soon, we have a break, but then we will be into our last talk, which will be slightly late in the day. We have not planned any sort of, okay, Misut, you have something to say? But
I will go out, so I will miss the last lecture. So that's why I would like to take this chance to thank you for the organization. It was very fruitful for everybody, I guess. So I personally thank you very much for letting us listen all these beautiful talks. I am glad to see you again, even online. I hope to see you in future again. Thank you very much.
Yeah, I think he has lost his connection.
I'm sorry if he couldn't hear this. So I gotta go. Thank you very much for the beautiful talk and for everything.
Thank you, Mr. On behalf of Professor Ghorpade, I also thank you for attending.
Thank you very much.
Thanks.
Okay,
thanks, Nirmay.
See you.
Thank you.
Thank you, Murmay, for your beautiful talks. It was very wonderful to listen to you.
Thank you.
So, Sartaj, we meet at now after half an hour, 20 minutes.
We'll meet at 8 o'clock. I think Professor Ghorpade has lost the connection.
Yeah.
So, we'll reassemble again at 8 o'clock for July's lecture.
Okay.
So we break for about 25 minutes now.
Okay.
We'll take a break. Okay, Murmay.
Okay, bye.
Bye,
Murmay.
Bye.
Hi. Hi, Chunlai.
Hi, can you see my screen?
Yes, yes.
Okay, that's great. And thanks again for organizing this excellent workshop. It's really interesting.
Thank you. Thank you for agreeing to participate and speak in this workshop. So you will have the last word, more or less.
Yes.
Yeah, and if you see Tor, say hi for me. Tor
Okay, yeah, yeah. Of course, I will. Yeah.
I know he's retired probably, but he's emeritus or something.
Sorry, I didn't hear you.
Hasn't he retired?
Yeah, yeah. He has retired. Okay, almost for 3 years. Yeah, but he has been very active, both in the research community as well and in our group. So he came to his office very often.
Okay.
Yeah, but due to COVID-19, since due to his age, so he's more conservative. But he said he would get the vaccination in April, and after that he will come to office more often.
Okay.
Yeah. Have you visited him before?
Well, we have met in many conferences. Both India, Europe. We even met in Tahiti once. It's long ago. But so yeah, I've known him for some time. We haven't worked together. So I've not been to Bergen, but I've been to Norway many times.
Which university did you visit?
I visit Tromsø.
I see. Yeah.
And Trygve Johnson is a collaborator.
Yeah.
Then, okay, I've also visited Oslo once or twice.
Yeah. Yeah, there are some strong group on coding theory in Norway. So
yes, certainly. Yeah, and Bergen is a very good group, I believe.
Yes.
I mean, at least I don't know the younger generation, but in the older people.
But now, I guess you also know Torleif Kleve, right?
Yeah, I know.
Yeah. I mean, Tu and Kleve, they have been very active in the past years, so they have set the flag for the same center, like the coding group in Bergen. Yeah.
So Klove has not retired yet, or has he?
He's older than Tu, so he retired 7 years ago.
Okay, yeah. There's Sartaj.
Hello, Chunlai.
Hello.
How are you?
Yeah, doing good.
Yeah, okay. Yeah.
I feel like I need to clean up my background.
Yeah. Yeah, I think I had some internet issues in the Brunmai's presentation. So,
Yeah, in fact, Masood was thanking you for organizing this workshop. Maybe you could not hear actually because
yeah, I partly heard. Yeah, but then I was disconnected.
Yeah.
All right. That's nice of you.
Yeah.
He works at the interface of commutative algebra and combinatorics and has some interest in coding theory. He's in Turkey, I think, in Ankara, I believe.
Okay.
But maybe a couple of years ago, we organized a conference in Istanbul. Myself, Peter Bilan, and Albasa, and Nurda Gulanbar. So he was one of the speakers. We had called him.
I see. Nardugul Anwar.
Yeah. She was a student of Peter Bilan.
Okay. I see. She also works on permutation polynomials.
She has some papers on permutation polynomials. Yeah.
It's a challenge to organize an online conference, especially in this.
Yeah, it's okay, but I think by and large it worked out well here.
Yeah. By now, I mean, it worked. The whole organization worked perfectly. But still, it's harder than organize normal physical conferences, and then you can, people can have more interaction with each other and.
Yeah, I'm maybe old-fashioned. I still prefer physical conferences and people in person rather than on a computer screen. But then I think we have to do the best we can in the given situation.
Yeah.
So the upcoming
most people, even you mentioned like even for younger generation. At least me, I consider I'm in the younger generation.
Sure.
We still prefer to have, and then we get chance to travel and to talk to different people and to get to see different places, right?
So BFA is going to be offline, the upcoming BFA, or
there is still plans to have physical conferences next year in Spain, but I feel like it's quite difficult. It's a little bit, regarding all the practical matters. It's not in Norway, it's in Spain, and since Spain is more like for the tourism country, so then even the COVID situation is better, then still there's a lot of uncertainties.
I see.
Yeah.
Yeah, sometimes people now, I see they're trying to go for the hybrid model. Partly online, those who can make it and want to come will come in person, but then some people talk online, etc.
Yeah, that's what we did for BFA this year. We don't want to cancel it, and also most of people, the participants are from Norway, and except for invited speakers. So then we invite speaker to give online talk, and all the local people in Norway, we went to a hotel, and then we booked a big conference room. So we had the physical room there.
Okay.
But for most of the talks, they are given online.
it's almost time, I guess.
Yeah. Maybe I can start so that we can
Sure.
try to finish on time.
Can start?
Yeah.
Yeah, please.
So should I start right away? Right? Yeah.
Yeah, I think it's 8 o'clock, so you can start.
Yeah. Yes. Okay. Yes. Okay. Then I can start. Welcome back, everyone. So I changed the title of my talk a little bit because I noticed most of the talks are about coding theory, and also personally I'm more into coding theory instead of cryptography. So I changed the slides a little bit and to give you more flavor about the decoding of some rank metric codes. Of course, in the slide in the talk, I will introduce some cryptography basics. Okay, the talk is composed of 3 major parts. In the beginning, I will introduce some basics of code-based cryptography. And in this part, I will mention the random syndrome decoding for Hamming metric and for rank metric. And then I will recap the macless crypto system for the Hamming metric. After that, then we will come into the rank metric codes with efficient decoding algorithms. These are required for rank metric codes used for cryptography. So we will use the 2 categories of rank metric codes and to build up crypto systems based on these 2 codes. That's the part 3. And in the end, I give a short summary of this talk. So let's first look at the cryptography. So, I noticed there are some talks on cryptography. It's just a recap. So here is a typical model of modern cryptography. So we have this encryption and the decryption part. And then if we want to encrypt message, we need to use some key. And for decryption process, we use some key as well to get original message. So we know that if these 2 keys used for encryption and decryption are the same, then it's a symmetric cryptography. That's for the conventional cryptography. And if these 2 keys are different, they are known as public key cryptography because one key will be kept public, known to everyone. And it's also called asymmetric cryptography since these 2 keys are different. Their role in the crypto systems are quite different. So for public key cryptography, before we introduce the one based on codes, then it's necessary to mention some requirements for public key cryptography. So first of all, we have the 3 stages of public key cryptography: the key generation, then encryption, and then decryption. These are 3 stages. So at the key generation, we need to have efficient process for generate the public key and the private key. Then for encryption, we require the encryption process should be efficient as well. And for decryption process, when we have the private key, then the decryption should be as efficient as possible. Well, regarding security, then it's quite typical that for an attacker, even the attacker knows a public key and some ciphertext, it should be difficult or computationally infeasible to determine the private key used for the encryption or the original message. So the first 3 are considered as the performance requirement, and the last one is considered as the security requirement. And for most of the public key cryptography, we know that they are essentially trapdoor one-way functions. So here, like for step 3 and step 4, for step 4 here, it's the one-way function. But when we have the private key, then we can calculate the reverse of the one-way function very efficiently. So this private key can be seen as a trapdoor for the one-way function. Here we use this computationally easy or computationally infeasible. That's kind of the terminology for algorithmic perspective. So if the process has a polynomial time complexity, we consider it computationally easy. When it has an exponential time complexity, we consider it the process computationally infeasible. So how can we build up public key crypto systems? I think all the participants here know that they are built up based on some difficult mathematics problems. For example, for RSA, it's based on the difficulty of factorization of big integers, and for the other public key crypto system like Algorithm or ECC, they are based on the discrete logarithm problem. Also, for the lattice-based cryptography, most of them they can seen as based on some hard problem like a shortest vector problem. Well, for code-based cryptography, the problem is the hard problem is the random syndrome decoding problem. And the security of such crypto systems is related to the hardness of the syndrome decoding problem for special metric. So here we will mention both Hamming metric and the rank metric. So let's start with some simple problems. So suppose we have a 4-rank matrix which has n minus k rows and n columns over FQ. And we have a vector S which has length n minus k over FQ. So this problem is asked to find the vector x such that this equation holds. Well, in fact, this problem, if we just look at it, it's a kind of simple linear algebra problem. So we have this 4-rank H, and then we are asked to solve these problems. And then since this H has a rank n minus k, so we know there are q to the power k possible x satisfying this equation. So it's relatively easy. And when we try to solve this problem from arithmetic way, then we can randomly choose like n minus k columns from H to get a submatrix. So with a good probability, this matrix would be an invertible matrix. Then in this case, we can solve this x just by here. Then how can we get more difficult problems based on this simple problem? The idea is we need to introduce some extra constraint on this on the solution x. So the widely used strategy is to ask or to require this solution to have a small weight for a certain metric. So if we are talking about Hamming metric, then that's a conventional or classic code-based cryptography, can be traced back in 1978. And when we talk about the rank metrics for the codes, then that's kind of the new algorithms and new crypto systems for this rank metric cryptography in recent years. Although the idea can be traced back to 90s. So let's look at this syndrome decoding problem. So here the task is we are asked to find a vector E such that this vector E satisfying this equation. Here we have this extra restriction that the E has a Hamming weight W, or smaller than the Hamming weight W here. And for coding theory, we know that if this matrix, this code, this matrix H associated with some well-known codes, such as read-Solomon codes or read-Muller codes or Gopa codes, or their variants. And then these parity check metrics have some special structure. Then in this case, we can come up with some efficient decoding algorithms with polynomial time complexity for this problem. Well, that's good news for coding theorists. Otherwise, if this edge has no clear structure, then it's computationally infeasible. The problem with this random matrix edge here, and since there's no clear structure, then let's see, okay, what if we try to use a brute force to see what's the complexity of this to solve this problem? Then since we know there are Q to the K possible solutions, then we can try this Q to the K possible solutions. Then we have this complexity Q to the K. So with W, then they all the n-dimensional vector and also brute force this type of these possible vectors. But here you see if this binomial coefficient n choose W from n, then in this case we have this n to the power W here. Then you see if normally Q is chosen as 2, then in the binary case, now you see this number is also an exponential of in terms of Q or in terms of n. So these two naive methods with the brute force attack didn't give us kind of polynomial time complexity. That's what we need for building up cryptography systems. But let's summarize this random syndrome decoding problem. So here, basically, we are given a random matrix H and a vector S, and we are asked to find an error vector or just a vector E with Hamming weight W here. This problem is proven to be NP-hard by Bellecombe and McAleese in 1987. And since then, there's a lot of crypto systems designed based on this kind of problem. And for this type of problem, the typical or best known attack is based on the information set decoding. And the basic idea is to guess the pattern of the support of the error. By support here, it means the coordinates such that the positions of the coordinates with which is non-zero. So this is the support of the error vector, and then use some pattern and try to assess the computation complexity, and then also to estimate its success probability. Based on that, so most of the information set decoding attack have the complexity for attacking this problem in this number. That's the Q to the power C times n. Here C is a constant. So it's the best known attack is around 0.0. That's 1/20. That's like around this number. So in any way, you see it's exponential complexity. And if we want to increase this complexity, then we need to enlarge this n, then to get the reasonably good security for crypto system. So suppose we have this good problem, then how can we build a crypto system based on this problem? Well, the idea is in fact not quite natural. For the encryption process, suppose we have a matrix or a code, and then we use its generate matrix. Then for the encryption process, we have the message, and then we generate the corresponding code word, then we add arrow on it. So then this C, that's we can consider received word in the language of coding theory. Then this is the ciphertext. So at the receiver end, the receiver wants to decrypt this ciphertext. So basically, the receiver needs to decode this ciphertext C. But in this case, the receiver or the whole design has to use some secret codes which has polynomial time decoding algorithm. And this has to be kept secret. This is considered as the private key for the receiver. So let's look at the McAlice crypto system. It's a classic code-based crypto system, and now it's in the third round for the NIST post-quantum cryptography. And the designers and the relevant researchers have developed this web page dedicated to McAlice crypto system. For audience here, if you are interested in this topic, then you can get enough and all the necessary information from this web page. The idea of McAlice crypto system is to use GOPA code to build up this crypto system. Here, suppose G is a generated matrix of GOPA code, which can be efficiently decoded. And here, suppose the error correcting capability for this GOPA code is T, which is much smaller than N. Then we choose two masking matrix. So the S and P, here S is a K times K random invertible matrix of FQ. P is N times N random permutation matrix. Then based on this S and P, these two masking matrices, the original generated matrix G is masked. Basically, okay, it's multiplied by S from the left and multiplied by P from the right. Then you have a new generated matrix. This generated matrix, we call it GPub. So this is a public key. And the original generated matrix G, together with the masking matrices S and P, are used as a private key. Then it's for the encryption, it's the same as what we have described. For the decryption, so we have the ciphertext and we want to get the original plain text. Then what we can do is first, the decryptor has the permutation matrix P. So use the inverse of permutation P. Then we have types it to the ciphertext C. Then in this case, C, since the C is equal to M times S times G times P, then we get this expression for this ciphertext. So here, because the permutation matrix P does reserve the Hamming weight of E, since it's a permutation matrix, it's just change the order of the coordinates in this arrow vector. Then it means the Hamming weight of this vector, this new arrow vector, is still T. Then in this case, by the decoding algorithm of GOPA codes, then we can decode this code word for GOPA code, and then we can find M S times G. That's the code word for modified GOPA code. Then in this case, we look at this MS and G. So then for the G, this original GOPA code generated matrix, we choose a submatrix GI here. Then we can type the inverse of GI and then times the inverse of S. Then you see here, by calculating this term, then we get the original message M. So that's the process of the decryption of McAlice crypto system. And since this one, the McAlice crypto system was invented, there have been a variety of different designs. Like it's a variant, and also based on some other decodable Hamming codes were proposed, and they are analyzed as well. And for most of the other variants, especially from other codes, the security of them are arguable, unfortunately. But it's very interesting that only the Macalis crypto system have been secure, although there have been many different attack attempts against it. So this is the kind of the very general overview of or the introduction of the code based in Hamming metric. Then what about the other metrics? So let's consider the rank metric. In previous lecture by Albert, he already mentioned a lot on rank metric codes. So here I just recap some basic definition here. And so in the rank metric codes, we mostly consider linear codes over fq to the n. Then first we need to define what is a rank metric. So here we have a vector in fq to the m to n. Then the rank of this vector is considered as the rank of the elements the coordinates a1 till an, which are elements in fq to the m. If we write these elements in terms of vectors over fq, then we get a matrix. Then the rank of this matrix is defined as the rank of this vector A. Equivalently, we can consider if we use this the coordinates a1, a2 till an to span a linear subspace, then the dimension of this subspace is the same as the previous definition of the rank. So this is a definition of the rank of a vector in fq to the n over 2n. Then, equipped with this rank metric, the NKD rank metric linear codes is defined as the k-dimensional subspace of this linear space, and the minimum rank is D. So we look at all the code words in this subspace, and then to get the minimum rank of the vector. So that's the rank here. So then we may wonder, okay, since we have this random syndrome decoding problem for Hamming metric, what about the random syndrome decoding problem for rank metric? In this case, we suppose we have this random parity check matrix H, but in this case, it's defined over fq to the n. So here you see it's colored blue to indicate the difference. Then we choose a positive integer w. That's the same for the Hamming metric case. Then we choose a vector s. In this case, it's a vector over f to the n. Again, we are asked to find a vector e. We can consider it as the arrow vector over fq to the n as well. Then the task is to find this arrow vector satisfying this syndrome equation. And here, this vector E needs to have the rank at most W. So if we look at this original rank syndrome decoding problem, it's more or less the same. So we change this Q to QM, and then here we replace the Hamming weight by rank metric. And it's quite natural to believe that this rank syndrome decoding should be an NP-hard problem as well. So it has been believed to be NP-hard for 2 decades. And recently, like back to around in 2015, and Gabriel and Zuma proved that this rank-based the rank syndrome decoding problem is a probable NP-hard with based on some probabilistic reduction to the rank syndrome decoding problem, the RSD problem. So based on this security proof of its hardness, then people have more confidence on the hardness of this problem. Then people have more confidence on using this hard problem to build up new crypto systems. Then if it's just like that, maybe it's not interesting enough. Then what is the advantage to use rank metric codes instead of Hamming metric codes to design a crypto system? Well, in fact, the most advantage is if we are targeting a security level. Let's say we want to have a crypto system to have 80-bit security or 128-bit security. Then in this case, if we are using rank metric codes, then we could have a much smaller key size. Why it is in this way? In fact, if we look at, suppose we consider a random code with these parameters n and k, and over f to the m, here normally n is assumed to be smaller than or equal to m. So if we consider this problem as in the Hamming metric case, then to decode errors with weight w would have complexity like in this format, in this formula, and it's close to. It's not easy to to estimate what's the exact of the complexity for these parameters. But in general, you see it's like the binomial coefficient divided by another smaller binomial coefficient. And as I mentioned before in the previous slide, so it can be considered as n to the power, like 2 to the power c times n. Here, where c is a constant around 1/20. But let's look at the decoding complexity for rank metric case. So this is like the complexity for decoding errors with rank w for this problem. And here, this paper is the very recent work. It's proposed by several researchers who are interested to attack rank metric crypto systems. And in their paper, they state that there are two cases. Here, I just list the one parameter, but just look at these two terms. You see here, it's a binomial coefficient divided by another binomial coefficient. But in this case, we have two binomial coefficients, and here it has an extra exponent. This is the typical matrix operation exponent. Sometimes people use omega, sometimes we directly use it, 2.6 something. And here, let's consider, for simplicity, let's consider as 3. But in general, you can see the big difference here. Here you have a binomial coefficient, and here you have this binomial coefficient cubed, and together with another binomial coefficient. So it means that if we choose the same n, then this one could be very big. It could be significantly larger than this complexity. In other words, if we want to target the same security level, then we can choose smaller n and m and k, these parameters for the code, for the rank metric codes. So these are the advantages of using rank metric codes for crypto system. Now, what are the requirements if we want to design a rank metric crypto system? Well, first we would like to have, and we in fact need to have a random-like behavior of the rank metric codes for good security. Another requirement is that we have to have decodable rank metric codes. Otherwise, we cannot decrypt the ciphertext efficiently. So that's a requirement. So then that's coming to the case like what are the decodable rank metric codes so far. In general, there are two types of decodable rank matrix codes. One is the Gaussian code. The other one is low rank parity check metric codes. So let's take a closer look at these two rank metric codes. So these two codes, the first one, Gaussian codes, most of audience here who are interested in rank metric codes would know this Gaussian codes quite well. And this low rank parity check metric codes was proposed by these 4 researchers in the conference WCC. Here it's interesting, like this conference we call it an international workshop on coding and code and cryptography, and then this WCC, that's a traditional workshop on code and cryptography. So it's interesting to present some of the work here. So since the rank metric codes decoding algorithms are a little bit complex, so I would like to introduce the strategy of decoding rank metric codes before we directly go to the specific codes. So here is the recap of the rank metric decoding task. So we are asked to decode to find the error vector E, satisfying this equation with the rank at most T. And in Hamming metric, for the decoding, for the information set decoding algorithms or methods, they are mostly look at the support of the error. In the rank metric codes, it's similar, but here in this case, the support of the error is defined in a different way. So here the support of the error vector is defined as the linear subspace spanned by the coordinates of the error vector E here over FQ. So suppose we can determine the error support E from the code. Then based on this support, then we can obtain a basis E1 till EW, since the error has rank W. So then the support would be generated by a basis with W elements. Then suppose we can get the error support, we can get the one basis of this error support. Then we can express the error vector, each coordinate of this error vector in terms of this basis. Then if we write in specifically, it's like we have this basis, and then for the first coordinate, then it's a linear combination of this basis. Then we can use like a matrix, a column, like the first column of X here. Then for the second coordinate, that's another linear combination of this basis. Then we take the second column of this X. So in this case, we can express E as the multiplication of this basis by a matrix over FQ, since it's a linear combination over FQ here. And then based on this, we can look at the original problem, then E times the parity check metric H equals S. So in this case, we can express all the elements here as the linear combination of over FQ. Now in this case, so originally we have n minus k equations. And by express all the elements in terms of vector over FQ, then for each equation, it leads to m equations. So then in total, we get n minus k times m equations. But what are the variables? Here you see you have E1 till ET, then we have this X. So it's here it should be W here. Then we know that since this basis is alone, then we have all the variables in X. Then we have W times N variables over FQ. So if the equation here the number of equations is larger than the variables, then this linear system is overdetermined with higher probability. Then we can solve these linear systems in polynomial time. And we can determine the coefficient here. And then accordingly, we can get the error vector. That's the idea of decoding rank metric codes. So now let's look at a specific example here. That's Gabdinian codes. The Gabdinian codes have been introduced by Albert in a previous lecture. Now here we can look at these codes, and the Gabdinian codes is considered as a rank metric analog of the Reed-Solomon codes because they have the same pattern in their code word, the representation. And since for Reed-Solomon codes, we have many or several decoding algorithms, then it's natural to kind of try to find the rank metric analog for decoding Gabdinian codes. So it turned out that there are several different efficient decoding algorithms for Gabdinian codes. Here I will just mention like the original decoding algorithm for Gabdinian codes. The other ones, they have a hidden connection with each other. So before we look at the decoding, let's look at encoding. Well, although it's simple, it's necessary to see how we get the code word from the message. So suppose we have message in length k, then by choosing n elements which are linear independent over fq, then we evaluate we use the message to construct the polynomial here. Then we evaluate this polynomial at these evaluation points. So then we get the corresponding code words. So for the first one, for the second one, then we get all the coordinates by evaluating this function at these points. So that's the encoding process of Gabdinian code. Then for decoding process, it's the whole idea is for the generator matrix of the Gabdinian codes, it has the pattern as the Vandermonde matrix form. Interestingly, its parity check matrix also has the similar pattern as a Vandermonde matrix. Then in this case, we can use this property to decode Gabdinian codes. Well, in general, for decoding Gabdinian codes, since it's MRD codes, as introduced by Albert, so we know that here the error correcting capability is d-1/2, and then here since it's MRD code, so d-1, I just write n-k here instead. So then let's kind of recap and to specify what are the steps under the strategy of decoding rank metric codes in general. So again, we have this strategy. We want to determine the support of the error defined in this way. So it's spanned by all the error coordinates, and it can be expressed by another basis with t elements. And suppose we have these elements, this base E1 and ET, then we define a polynomial, a linearized polynomial, which vanishes at all these bases. Then it means if we take all the linear combinations of these bases, then this polynomial would vanish at all these elements as well. Then in this case, we can get a linearized polynomial which vanishes at all the elements. So it means that lambda of x vanish at the error support. So although we don't know this E1 and ET, we have this property of this lambda of x. Then we have this syndrome coordinates Si. Then we use it to define a linearized polynomial S of x. So thanks to the Vandermonde structure of the parity check matrix, it's interesting. It's similar as the read-solemn codes. We can obtain a key equation here. This key equation, it's given in this form. So lambda x compensated by s of x, then modulo this monomial will be f of x. In general, here, if we consider just look at the modulus here, it has a q degree n minus k. But here due to this structure, we know that this fx will have the q degree smaller than t, which is much smaller than n minus k here. It's kind of the half of n minus k if d is the limit of the error correcting ability. So due to this due to the time limit, I went looking to how this key equation is obtained. But for some of you who are interested, then you can read it afterwards. And we can skip here. And based on this pattern of the composition of these two polynomials, then we can have some linear equation system, or in other ways, here we can look at it from the extended Euclidean algorithm perspective. So here we have s of x and x q to the n minus k, these two polynomial, and we are asked to find its greatest common divisor. Then we have this lambda of x as its coefficient, and f of x as their greatest common divisor. But here we are only interested in the coefficient lambda of x here. And if we can find this lambda of x based on sx and this monomial, then we can solve this lambda of x to find all the roots of it. Then we can find a basis E1 till ET for this error support. And based on that, the remaining part is it would be simpler, and it's a kind of quite routine steps. Then we can solve this S by hereby we first look at it, and then we can find the coefficients. Then based on the original syndrome equation, then we can with y, then we can find x. Then with x, with the basis E1 to ET, then we can get the original arrow vector E. So in general, the decoding complexity of Gaussian codes is this is worst case. It can be optimized to like a sub-quadratic complexity. Let's look at another decodable rank metric codes. It was proposed by Gabriel and his co-authors in 2013 in WCC. So here the idea of design LRPC codes borrows idea of LDPC codes. And here we suppose we have integer d, which is considered as a low rank. It is smaller than much smaller than n or much smaller than k here. Then we define four rank parity tag matrix H, and suppose for all the elements Hij in this matrix, then we use these elements to generate a subspace over Fq. And suppose this subspace has a dimension T, which is much smaller than n, then we consider this code is a rank metric is a LRPC code. And here is here I think it should be D here. It's a typo. But anyway, you get the idea. So the dimension of the subspace F is smaller or equal to D. So it's upbounded by D. Then let's look at the decoding algorithm of this LRPC code. Again, the strategy is to find the error support. So we have this this error support. Then we defined it. Again, it's the same notation here. We want to use this basis to determine E. So we will only look at how can we find the error support here. Okay, and this some key observation based on the restriction of the rank for the parity check matrix. So if we look at the syndrome equation, that's S equals E times H transpose, then we write this E1E as E1 to ET times this matrix over FQ. Then we have this equation. So here, if we look at the H of T, since X, the matrix is defined over FQ, so the whole, this part, they can be considered as an element in F. So for H here, or for H times this one, it can be considered as element in F, this subspace generated by H of Hij. And if we look at the syndrome S here, the S can be seen as generated by the coordinate S1 till Sn minus k. So based on this equation, we know that Si, each coordinate, has to belong to this subspace. Here, what's this subspace? This one is a basis, and we consider another basis. So since S can be expressed by in this form, it means, so if we consider the product of the subspace here and the subspace here, so it means S will be always in the product of these two subspaces. And what are the bases of this two subspace, the product of this two subspace? In fact, we just need to consider to take the basis for each subspace. Then we times them together, we get a subspace. This subspace, we can write the possible basis as E1 times F1, E1 times F2 till ET times FD here. So here, Si will be always in this subspace. Then if we use the coordinates of syndrome S, then we see that from here, we know that the subspace of a syndrome coordinate will be always a subset of or a subspace of this product subspace. So interestingly, if here we choose n minus k, we know that this subspace has dimension at most d times t, because some of these elements here could be linearly dependent. But in general, we know that the product subspace will have dimension at most d times t. Here we know that this, if we randomly generate this syndrome, then the dimension of this subspace would be n minus k. Sometimes could be smaller, but with higher probability, it will be n minus k. Then in this case, if n minus k is larger than the t times t, then we know that these two subspace will be the same, right? And based on this observation, then let's see how we can use this observation to get the error support. So assume here I keep this assumption in bold fold, and here suppose the syndrome subspace is equal to the product of this subspace. Then since here, from here we know that E will be belong to this one. So because here this arrow vector E, the arrow subspace E will be belong to this one. But more specifically for this subspace, if we times all the elements by Fi here, suppose let's say F1, then we get, okay, E1, then E2 for the first T elements, it will be E1, E2 till ET. And then we have some other elements. So it means that E, this arrow support, will be always a subspace of this one. And if we choose F2, then we get for the next T elements, we get E1, E2 till ET. So it means this arrow support will be always a subspace of Si defined in this way. So it take the it multiply x element by the inverse of fi here. Then we can intersect this subspace, and with a good probability that if we intersect all of them, then if the resulting subspace has dimension t, then we know that the error support will be the intersection of them. So when we try to intersect them, then if we get at some point we get the subspace with dimension t, then we know that, okay, then we find the E, the error support. Then based on this error support, we can solve this syndrome decoding problem. That's the idea of LIPC codes. Here, because it's an assumption and it's natural that this assumption could be invalid, then we need to estimate its error probability of this decoding process. In this case, we know that if m minus k, this is a requirement. If m is large compared to d times t, then the error mainly comes from like the dimension of the syndrome subspace is smaller than d times t. In this case, the probability would be like in this one, you see it's when n and t, when n and k is chosen large enough, or in the other words, when t is much smaller than n minus k, then this probability could be quite small. So with these two decodable rank metric codes, then let's see how the some crypto systems are built based on these two rank metric codes. The first one is based on the Gabinian codes. Before that, again, I will give you an overview of the idea here. It's quite similar as code-based crypto in Hamming metric. In this case, for the key generation process, we have the private key, which is an NK rank metric codes with T error correcting capability. It means this code can correct errors up to T with rank up to T. Then we try to find a transformation on the code word. This transformation should be linear and should be preserve the rank of the code word. So then we simply call it a rank asymmetric linear transformation. Then on the code, then here we get by applying this transformation, we get another code. This code is used as a public key. And the original this code and the corresponding decoding algorithm is considered as the private key. Okay, so then for encryption process, it's again, so we have m times g plus e, that's the encryption process. For decryption process, it's essentially the decoding process when we have the private key. When we don't have the private key, then it's a general random rank metric syndrome decoding problem. So it's known to be NP hard. Now when we have this L, this transformation, then since this C prime, this C is a code word, then if we apply this inverse of this transformation on this C, we get a new code word. This C prime would be a code word of the original code C here. Then in this case, we can apply the decoding algorithm on this C prime. Then we can get original message M. So let's look at the first rank metric based crypto system, which was proposed by Gabdulin and his co-authors in 1990s. So it's a rather old rank metric based crypto system. Here, the idea is quite similar as what we have described. So we use the Gabdulin code C here, and suppose its generator matrix is GK. And to hide this matrix, then we need to use some other matrix. In the design of GPT crypto system, they use two matrices. One is called distortion matrix X to enlarge the codenames. And the other one is this masking matrix P, which is an S, like it's the same as the MAC-Alice crypto system. Then it applies P and S on both sides. And for the original Gaussian code, suppose the error is t smaller than t minus 1 over 2, then we can use the decoding algorithm of Gaussian codes. And let's see the GPT crypto system. So the private key is this G, S, and P as also an X. And then here we have the public key, that's this mask the generated matrix G, then we denote as G prime. So for encryption, you see it's the same, but here we know G prime is a masked matrix for the original GK. Then for decryption process, then we have this error, we have the P. First we have the P, then we apply the inverse of P to the ciphertext. Then we get a code, we get a word that is decodable by the decoding algorithm of Gaussian codes. And to make it more secure, the designer used X to extend the length of the code. And here we have this Q part of the error, but still the plus of them are decodable. In this case, we can get the message by using the decoding algorithm of Gaussian codes, as long as we have the original matrix G and S. Here it's a type, it should be P. Well, this is a GPT crypto system. The advantage is the same as all the rank metric codes. It should have shorter keys than the classical code-based crypto system like MAC-Alice crypto system for Hemi-metric. But the disadvantage here is because the Gaussian codes have very strong algebraic structure, so it leads to some serious security issues. It turned out that Orbeck proposed a structural attack on GPT crypto system in 2005. And this type of attack can be applied to all the variants of GPT crypto system. So in principle, this design is broken under this attack. Then the second one is this LRPC-based crypto system. The advantage of using LRPC-based crypto system is that the code itself is randomly generated. Then in this case, the structure of the code is much less strong than the Gaussian codes. Or in other words, we can see the problem based on this code would be rather close to the random syndrome decoding problem in rank matrix. So that's a good news for designing crypto system based on these codes. So the idea is the similar, and in this case we have the key generation that to generate a matrix H, which is used as the parity check matrix for LRPC codes. And based on that, we only need to use another masking matrix, just one, because the matrix itself is already pretty random. Then here we have the private key, that's original parity check matrix of LRPC code, and masking matrix R. Then for the public key, then we have this R times G, that just the masking on the left, then we get the public key. So for the encryption, it's the same. For the decryption, it's similar. We apply this the inverse of R, then we can get the decodable word for LRPC codes. Based on this idea, this crypto system is rather basic, and based on it, this crypto system has been extended to two strong crypto systems. with these two systems have been submitted to the NIST proposed standardization of postal quantum cryptography. So it's a Rollo. In the first round, there are 3 similar crypto systems, and in the second round, they are merged to one crypto system. Another one is RQC. Sorry, here it should be RQC. It's RQC. These 2 crypto systems are the crypto systems succeeded in the second round of NIST postal quantum cryptography. For some of you, if you are interested, you can check all the information of these 2 systems at these 2 web pages. So to summarize what I have covered in this lecture, so we have introduced the idea of using random nuclear codes for building up crypto systems. And for rank metric codes, we have introduced the GPT, and then we also mentioned the LRPC-based crypto system, which is used to extend it to Rollo and RQC. And the reason we can use it because these 2 types of codes have efficient decoding algorithm. I consider it's a quite young and active area for researchers and for students. So there are a lot of work to be done. One example is whether someone can find new rank metric codes with efficient decoder algorithms. In this case, we would be able to apply these codes for rank metric cryptography. With that being said, I think it's a good point to stop here, and I would like to thank the organizers for the excellent workshop. Thank you very much.
Thank you, Chinlai.
Yeah,
thank
thanks.
you so much. Yeah. Sartaj, you want to say something?
No, actually, I was just looking at the chat box. There are no questions as of now.
Yeah.
Yeah, if there are any questions, feel free to ask.
Sir, I have one question.
Yeah.
We have described the disadvantage of GPT, sir. Sir, in one way we say that it has a strong algebraic structure.
Sorry, I cannot hear you clearly due to the connection.
Sir, we say that GPT has strong algebraic structure.
Sorry, I still can't hear you properly.
On the chat box?
Slide number 33, sir.
Number 32?
Slide number 33.
Yes, sir.
Yeah. Yes.
Second line. Here we write in second line, sir, disadvantage.
Yeah.
Here we write strong algebraic structure. So, if it has strong algebraic structure, then what is short issue, sir? How we...
What?
Why is that?
Sir?
That's what he wants to ask, I think. Is that correct, Pawanji?
Please repeat, sir. I am not able to...
Are you the question you want to ask is, why is strong algebraic structure a disadvantage? Or why is that giving right? I think that's the question.
Well, due to the time limit, I think I can understand like in very general way. If you consider the problem that we use to design crypto system is we want to have a random metric codes, then we can use these random metric codes to use the hardest of the problem to build up crypto system. But when the code used has rather strong algebra structure, then it's very difficult to convert this code to random codes. And although you can, a typical way is to use some metrics on both sides to hide the original codes, but still it's not easy to be done, and the structure still remains in some pattern, and this pattern can be used by attackers. Then this is the idea of the structural attacks by overback. So I mean, in high-level language, you can consider the random generated codes and the calculated codes. They are kind of far away from each other, and it's not easy to try to convert it to code that is very close to random code. I mean, if you are interested, you can check out this paper, and because it's quite technical and it's not easy to explain explicitly what the disadvantage here.
Okay.
Sartaj, you are muted.
Okay. So there is a question in the chat box. Is there any link between codes and secret sharing schemes?
Codes and secret sharing schemes? Yes, I think so. And especially for Hamming metric, they are having some research on using few weight metric, few weight linear codes to design secret sharing scheme, and the idea can be traced back to 1990s. And based on that, there are a lot of work. But the most focus of using codes for secret sharing scheme is to find linear codes with a few non-zero weights. That's a major focus, as I know.
Yeah, may I ask something?
Yeah. Yes, of course.
Yes. This McEllis crypto system has some advantage over RSA, no? Because RSA is future security. Depends entirely on the advances in factoring techniques.
Yeah.
So with respect to that, maybe McEllis we can use at that time over RSA.
I consider for most of this code-based cryptography and also lattice cryptography, it was promoted by the Peter Shaw's quantum attack on RSA and on the discrete logarithm problem. I mean, if you are aware of some of the research in recent years, since 1993, when Peter Shaw proposed the quantum attack on number-theoretic problems like RSA to factorize big integers with quantum computers in polynomial time. I mean, regarding that, so all new public key cryptography systems which aims to resist against the attack of the Peter Shaw's paper, then it will be welcomed, right? That also promotes why the least standardization of post-quantum cryptography.
It's faster than maybe.
Yes, I agree with you. Yeah, it's also faster. Yeah. The problem is the key size of McEllis is rather big, and some people don't like the size. Yes, I agree with you. It's a lot faster than RSA, both for the encryption and the decryption.
Thank you.
Okay. Any other questions or comments? Sushil Azad has thanked you for giving a simple and very good coverage.
Thanks, yeah. Thanks for staying with me for the last talk.
So I guess, yes, indeed, it is the last talk, and it's our pleasure to thank all the speakers and most importantly also all the participants, who stayed with us at different hours in different parts of the world and participated very actively. Thank you very much. If you have any feedback, you can just write to us at the general address. I think we are not having a formal valedictory function or anything like that. But nonetheless, we are grateful to our speakers and participants who, I think it is fair to say that have made this workshop a success. Thank you very much.
Thank you for organizing the workshop.
Yes.
Sir, can you say something about participant certificate?
Oh yeah. Okay. There are several of you, wanted a certificate of participation and have paid the registration fees. So, and I think some of you have also expressed the concern that they want to make sure their name and affiliation appears correctly in the certificate. Of course, that's important. So what we are going to do is, to those of you who ask for a certificate and paid the fees, we are going to send you a Google form in which you get one more opportunity to write correctly your name exactly the way you want it to appear on the certificate, and your affiliation the way you want it to appear on the certificate, and then we will have it made, and it will be signed by all the organizers and sent to you by email. And if you actually need a hard copy, maybe you can write to us and we'll see if we can also send you that. And along with the certificate, we will also send you an invoice for the payment that you made. So if you need to claim it from somewhere and so on. Other than that, if there are any questions, just write to us. Thank you, and have a nice weekend.
Yeah. Bye, everyone. Yeah.
Bye.
Thank you.
Thank you, Arun, Sartaj.
Thank you, sir, for
Thank you, sir. Thank you, sir. Sir, we must thank you very much, sir, because of you only we could do this.
Yes. Yes.
It's a collective effort. I mean, everybody chipped in, so good.
Yeah. Thanks, Sudhir, for me that.
Yeah, I mean, in fact, you joined at a short notice and really actively participated. That's we appreciate that.
Thank you.
Thank you to all of you, sir. I'm Ritesh Kumar, and I am in the earliest stage of the research, and my research will be further studies on this coding and some cryptography, and I have benefited with this workshop a lot.
Hey, I'm glad to hear that. All the best to you, Ritesh.
Thank you.
Sir, I have one emotional thought that समय का पता एकदम नहीं चला पूरे
क्या बात है
कितनी जल्दी 5 दिन बीत गए ये एकदम पता नहीं चला सर
बात है
हमारे सरताज भाई भी बड़े शायर हैं वो भी एक शायर थे देखा था
Thank you.
Sir, may I say something?
Yes.
Sir, I am Sudhamsu Ranjan. I have done my MSc from Ranchi University, Jharkhand. And I want to carry out my further studies in this area. And this workshop will be much helpful for me. The experts from different fields gave me a great exposure about this field. And I am very much thankful to the organizers for such a wonderful workshop.
Thank you. Thank you so much. All the best to you.
Thank you, sir.
If anyone else would like to say anything, please unmute yourselves.
I will mute. Hello. Yes, sir.
Yeah, I want to just thank everyone, every speaker. The last 5 days were wonderful days. I enjoyed every talk, and nonetheless, I think that even last one, well, no one was less, I feel so. Okay? It was a great workshop.
Thank you.
Congratulations to all.
Thank you, sir.
Thank you. I said, my battery is going low, so I leave. And thank you. Thanks again, sir.
Okay, sir. Okay, thank you. So, should we close it? I know it's late in the day, so people need to sleep or eat their dinner and so on. You're muted, Sataj.
Yeah, so what I was saying, maybe we can close because I think, yeah.
So Alberto is there. Okay. All right. Thank you. Good night.
Okay.
Thank you, sir. Thank you very much.
Thank you very much.
Thank you, sir.
Okay.
Bye.
Bye, sir.
Bye, sir. Bye. Bye. Bye, Sataj भाई.
Bye. Okay.
कल बात करते हैं.
Okay. Okay. Okay.
शायद गुरुजी लेफ्ट हो चुके हैं.
Just a minute. Let me see. I think he has left the meeting.
Pancho, yes. Alberto is there.
Yeah. Several others are there. At least I can see 9 people are there. So
5 are there. Anto, Alberto, Tulsi, Nazim. You are 2, and Sonali Batra are there.
Yeah, actually, one of my login is from the actually department. So during the break,
ठीक है फिर मैं क्या बोल रहा हूँ कल ही बात करते हैं फिर. Okay. Have a good night.
Okay, you too. Thank you so much.
Thank you.